This is your chance to master logistic regression for free with Anjali Pandey, a data scientist at Accenture. Welcome to Newton School's live Logistic Regression Bootcamp, a beginner-friendly, hands-on session where you'll learn the foundations of classification and build your own first logistic regression model step by step. Whether you're a student, a beginner in machine learning, or a professional exploring AI, this live session is made for you. And remember, don't just watch, build along life. Code as you learn and practice in real time. Want more practice? Head over to Newton School Launchpad. The link is right there in the description. Let's dive in and start coding with Anjali.
There are two types of um, logistic regression problem statement. Logistic regression problem statement. First is your binary class classification. Binary class classification. If I have to give you just some examples, I think we spoke about the examples for this as well. Spam classifier. Spam classifier, then we have fraud detection as well. Fraud detection as well. There can be other examples as well. For example, cancer detection or any other example you can take wherein in the target variable you only have two distinct values. That is your binary class classification. So I'm going to put like this. The another type that we have in logistic regression is your multi-class classification. And when I'm talking about binary class classification and multi-class classification, this is not just limited to logistic regression. It is applicable to any type of classification problem that you're going to solve. Even if, for example, you're using decision tree to solve a classification type of problem statement, there also it can be only of two type, either binary or multi-class. Okay, these are the only two possible ways that you can solve this kind of problem statement for classification. Now let us go back to the PPT. And then we just did a brief short introduction about what exactly is logistic regression. And then we have to now talk about how it works. So I'll start with just a small example we'll take, and then we are going to talk about how exactly logistic regression works and why do we call it regression despite the fact that it does not solve regression type of problem statement. Logistic regression. What is logistic regression? Logistic regression is a supervised machine learning technique using which technique, using which what kind of problem we can solve? We can solve classification type of problem. Classification problem statement. Classification problem statement. That's it. If anyone asks you what exactly is logistic regression, if you're able to say only this much, that is more than sufficient. You don't have to give any bookish definition or anything like that. Just this much is more than sufficient. It is a supervised machine learning technique using which we solve classification type of problem statement. That's it. Now, what kind of data we have when we are trying to solve classification type of problem statement, and this is not limited to logistic, this is for any classification type of problem statement. In your data, you will the type of data in your target variable will be categorical in nature. Categorical means that it can only take certain distinct values or certain unique values. Probably, for example, if I have to give you good better best, good better best. So, for example, if I have transaction based data and I'm trying to understand if I can give loan to certain customers and basis their transaction and their credit history, I'm trying to give them a rating or something like that, where I'm saying that, okay, the credit score is good, it's better or best. I'm just categorizing in these three variables. Then this type of problem statement will become my uh, multi-class classification because we have more than two distinct categorical value in the target variable. So this is one example. There can be many more examples which we'll try to see. Now, so let us say, I think I also spoke about in the last class, what is the problem that we face when we are trying to fit in a straight line on a data which is not separable by a straight line, right? So I think I took an example wherein basis the age of people, we are trying to predict whether that person can vote or cannot vote, right? So this is a simple problem statement that I had taken, and I had also created this kind of graph where here I have this value can vote value is 1, can't vote can't vote value is 0. Now we had set a threshold value at zero point 0.5, and basis that we had made a decision that okay, here somewhere I'll have age 18. So what we are saying is that we'll make a rule that anyone whose age is greater than 18, those data points will lie over here, whereas anyone whose age is less than 18, data point is going to lie over here. And by looking at this kind of distribution and this graph, anyone can predict that okay, whether this particular person whose age is over here, will they fall in this class 1 or class 0. So this is how you can do the prediction. So researchers, when they started working on logistic, they said that okay, let us do one thing, let us try to use the line of best fit to predict on this kind of data distribution as well. So let us say this, I think I've drawn it a little further. So I'll just, okay, let us say this is the line of best fit. And here I can see that at age 18, we are getting a threshold of zero point 0.5. So what we can say that if greater than zero point 0.5, okay, if greater than zero point 0.5, we are going to say that can vote, else can't vote, can't vote. We can create a rule based system. Using that rule based system, we can make a decision or we can get a prediction out of this line of best fit using this rule based system. But the problem comes when a outlier data point comes in. So let us say that a person whose age is 100 or 120 or whatever it is, a outlier data point has come in. Now, because the difference between the actual and the predicted value will be very far away, what this line of best fit will do, it will try to shift, it will change like this to accommodate this data point as well, so that it can make decision for that data point as well. Now if you will look at this and if you'll try to understand basis this rule based system, you can see this threshold value has now shifted to a higher age value. Corresponding age has now become higher, so probably this is, I would say, 35, let's just assume. Now what we are saying is that if now we are classifying people whose age is more than 35, we are only classifying them as they can vote. Other rest, everyone, we are classifying as cannot vote. This is misclassification. All of these data points are now getting misclassified. What I said is that if we have outlier in our data, because of that outlier, our line of best fit will try to shift. Because what is the role of line of best fit? It will try to reduce the error between the actual and the predicted value, right? So to reduce that error, it is going to shift and get closer to this particular point and closer to the distribution as well. Because it shifted, now the threshold value has changed. For the same zero point 0.5 threshold, which we have written in the rule based system, we can see that the corresponding age is now higher. Now this rule is not going to work. Why? Because if I'm going to use the same threshold and same rule, now I'm saying that anyone whose age is greater than 35, only they can vote. I'm saying that these people cannot vote, which is wrong. We are misclassifying this set of people just because my line of best fit shifted. This outlier, so this outlier is one of the problem that researchers came across, and they decided that we cannot use this line of best fit or a straight line to do a prediction for a classification type of problem statement. The other problem is that if you will see, a straight line can extend beyond this as well, right? So but The type of output that we can get in classification, it can only exist between 0 and 1. It cannot extend 0 and 1. Here, by looking at this line, we are seeing that the predicted value can even take negative values, and the predicted value can even take values higher than 1, which cannot happen clearly. So this is also an issue. The extended boundary of straight line, boundary of straight line. This was another problem that researchers came across when they were trying to use straight line problems with line of best fit. With line of best fit, they were trying to use straight line, the linear regression line, at the line of best fit, and they came across these two problems. That is when they decided to solve this. How can they solve it? So they came across a very useful mathematical function which is called as sigmoid function. Sigmoid function. Sigmoid function, gradient descent, these are the two topics that I said in the last class as well. These are going to haunt you even until deep learning. In deep learning, more often you're going to come across sigmoid function or gradient descent. Now, what this sigmoid function does, the mathematical equation for this sigmoid function is, so 1 upon 1 plus e to the power negative of z. This is the mathematical function of your sigmoid, and this is how you represent your sigmoid function. Now, researchers said that, okay, we will take the equation of, we'll take the equation of line of best fit, y is equal to mx plus c. They're replacing this y with z so that they can put it over here. More or less, it's the same thing. What they said is that we need to squash that straight line because it is extending beyond 0 and 1. We need to squash it. We need to cut it from here and here. To cut that straight line, they used this sigmoid function. What this sigmoid function will do, it is going to cut the boundary of this straight line so that it lies only between 0 and 1. Now, next, what you have to do is you just have to put this e raised to the power negative of mx plus c. That's it. Now, if you're going to plot this mathematical equation, if you want to plot it on a xy axis or a graph, two-dimensional graph, you are going to get something like this S-shaped curve. So it will be a curve like this. It will be nearer to axis. So this is your axis. Let me just change the axis here. This S-shaped curve you're going to get when you will plot this equation that I've just written. Now, this S-shaped curve is going to lie between 0 and 1. The minimum value that it can take is 0 and the maximum value that it can take is 1. Now, this clearly solves the problem that researchers were facing when they were trying to use straight line as the line of best fit for solving classification type of problem statement. So let us go back over here and let us try to look at this graph. As you can see here, what we are doing in logistic regression, the type of mathematical graph that we get is a S-shaped curve wherein the minimum value that it can take is 0 and the maximum value that it can take is 1. I'll tell you the reason why we needed to have the values between 0 and 1. The predicted value had to lie between 0 and 1 always, because let us take an example of binary class classification, spam classifier. Spam classifier. The output that you can get in this kind of machine learning algorithm is either spam or not spam. Not spam. Now you can convert this into a mathematical form and you can say that this is my class 0 and this is my class 1. Okay, this is how you can represent it in a class form, and usually you can switch between this or this. Whatever you feel comfortable with, you can use. But when you get the prediction for your spam using machine learning algorithm, the prediction is not 0 1. It will always be probability value. Probability value. Okay. And we all know that probability always lies between 0 and 1. Right? Any probability value will lie between 0 and 1. That is why we needed, and this is not just applicable for binary class classification, also for multi-class classification. The prediction that you're going to get from your logistic regression or any other model that you will use to solve classification problem, it will be a probability value, and probability can only lie between 0 and 1. So for example, if I talk about this, let us say that your model has predicted the probability that given that data point, the output that this email is a spam, the probability is, let's say, 0.4, and the probability for that particular email to be not spam is 0.6. Point 0.6. This is how you're going to get the prediction. Now it is up to you to convert these predictions into the class label. How you can convert that? Using a threshold value, you can convert it, right? So we'll talk about how to convert that probability into the label. We'll talk about that in detail later on. But right now, it was important to understand why we needed this kind of mathematical representation for classification type of problem statement, because the output is a probability, and probability can only lie between 0 and 1. Let us go back to this graph. Okay, now I think we have seen this as well. So here, initially, you would start with a data wherein in that data you're going to have different features. For example, if you're doing some prediction, definitely you'll have certain set of columns or features. You can call it whatever you want. Now you have to do your pre-processing. You'll have to do your feature engineering or whatever you want to do. On top of that, you can do that scaling or doing univariate, bivariate analysis, imputing null values, dealing with outlier. All of that you can do on your data. That will remain same. Now, initially, if you try to represent it using a linear combination of the features, you can use a straight line equation. This is what researchers started with. They used y is equal to mx plus c kind of equation, which is exactly what you're seeing here. Just that this is an extended version of y is equal to mx plus c. That is why the equation looks a little bit like this. Now, researchers applied sigmoid function on top of that so that they can get the prediction output between 0 and 1. They wanted to limit the range of the output. That is why they used sigmoid function. And when they used sigmoid function, they got this kind of S-shaped curve. And basis this, now whatever prediction you're going to get, that will be your classification model output. Then definitely you'll have to train your model and you'll have to get the prediction. This is how you're going to solve a classification problem. Mathematics behind it is only this much. We'll talk about the evaluation, the cost function for this. It will be different. How you evaluate a classification, that is going to change, but we are going to talk about all of that. What are the problems in classification type of problem statement? That is also going to change. So we'll talk about all of that. Now, let us talk about the applications. Some of these applications we already have seen, but let us talk about that. Medical diagnosis. Now, why we are calling this as classification problem statement? Because, for example, if you want to predict, given certain biological features of a person, you want to predict if that person has cancer or not. So, the output can only take two values: has cancer, does not have cancer, right? Only two possible output values can be there for that model. So it's a binary class classification. If you're trying to probably predict different variations of tumor in a person, does he have brain cancer, does he have uh, other type of cancer, right? So in that case also, that is a classification type of problem statement. All of that is going to fall within medical diagnosis. Spam detection, a very common problem, and I think everyone at least once in their life works on this problem statement when they are starting out logistic regression, and a very common problem or a very common project in resume. Everywhere you're going to see this. Now, given a certain attribute for a email body, you can determine if that email is spam or not. We all are using Gmail. In our Gmail, whenever an email comes in, it automatically classifies that as a spam or not spam. Because if Gmail thinks that, okay, this email looks like a spam, it will send it to spam folder. Otherwise, it will keep it to the normal folder. How that is done? No human is going to sit behind and do it for you, right? All of that happens because there is a model that has been trained to do that prediction, and automatically all of that gets done. We'll see what are the different features that you can take a look at, and all of that we are going to talk about. Customer churn, a very important problem statement. A very, very important problem statement: churn prediction. Even in my team, when I had just joined, I started working with this. This was the first problem statement that I had solved in my team. Churn prediction is very important for marketing. So, for example, if you are working in a marketing in a team where marketing is one part or one pillar of the team, nobody wants to spend a lot of money in marketing or advertisement. So, cost is a very crucial factor in marketing or advertisement. Now, I'll take an example of Netflix. Netflix. We all subscribe to Netflix or other OTT channel, for example, Disney Hotstar. It can be any other OTT platform, Geo, whatever that is. In Netflix, let us say that I had subscribed for 1 month. After 1 month, I discontinued the service. I was no longer a customer for Netflix. Now I have become a churn customer. Churn customer. Churned customer is a customer who no longer avails service of a particular platform or product. So that is your churned customer. If you discontinue using certain set of services, you become a churned customer for that organization. In this case, Netflix. Now, to acquire a new customer, it is going to be very costly compared to retaining the existing customer. So, always, if you are able to predict which customer is more likely to churn, you will probably be able to retain that customer before the customer decides to leave. In that case, eventually you are saving lot of cost. Advertisement is very, very costly. Acquiring a new customer is very, very, very costly. So if you can build this kind of model, you will save a lot of revenue for the business. That is why this is very important. Now let us see the other applications. So we have credit scoring. This is where I had taken an example of good, better, best. So credit scoring prediction. Credit scoring prediction. In credit scoring prediction, for example, you have the data points like salary of a person, salary of the credit history. If someone has not paid the EMI or installment timely, you'll have information with respect to that as well. Any family dependency. For example, if you are the sole earner of your family, then your family is dependent on you. If you are marital status, if you are married, you have children, then definitely it will be taken as a different uh, credit scoring method. Let me just change this. Let us say we have these kind of feature. Using these features, we are trying to understand what is the credit score credit score for a particular customer. Basis this feature, and basis that we are trying to determine if the customer falls in good, better, or best. Good, better, best. Okay, so whenever people who are falling in this particular segment with respect to credit score, we are going to approach them for any new offer, any new loan offer, right? If a new loan offer comes in to a particular bank, this segment of people will be the first ones to be notified about these schemes, right? This is how you can utilize this kind of model. Let me go back here. I think fraud detection, we all know. Given a set of transaction related features, if you're able to predict if a transaction is fraud or not fraud, what kind of classification problem this is? This is your binary class classification problem statement. And the last is sentiment analysis. Another very common problem and something which I have worked on as well. Sentiment in my current role at Accenture, sentiment analysis. I have worked on text type of data. So I've used natural language processing for this, but you can solve this kind of problem even using machine learning, supervised machine learning technique. It's just that the kind of accuracy that you're going to get will totally depend on the data that you have. And in my case, the data that I had, it was not able to get good accuracy just by using simple machine learning techniques. So I decided to go ahead and use deep learning and other advanced techniques. And definitely you're going to use natural language processing if your type of data that you have is a text based data. Now, what exactly is sentiment analysis? For example, we all shop from sites like Amazon, Flipkart. or Myntra or any other company for that matter. Flip, I think I've written wrong spelling. Flipkart. Okay, all of these platforms, for every single product, if customers have bought it, they would have definitely reviewed that and given some kind of rating, right? Or probably would have written some comment as well. Product, you will see the comments as well. Some of those comments can be positive. So for example, if you're buying a iPhone from Amazon and you got iPhone in a very new quality, or it was really good, it worked really well for you, you'll leave a positive comment, right, on the feedback or the review page of that particular product on Amazon. But if your experience was not good for a given product, you're going to leave a negative comment saying that this product was useless, not worth the money, and all of that, right? That's a negative sentiment. In some cases, the sentiment can be neutral, right? So whenever you're doing a sentiment analysis, the output or the prediction that you're going to get will be these three. Either the sentiment behind a feedback is going to be positive, or negative, or neutral, right? It will depend. If probably some stakeholders would want to add any other distinct output, then they can do it. But usually you will see only these are the different output variables that can come in this. So what kind of problem statement this will become? Multi-class classification. Multi-class classification, right? Okay, now let us go back here. Let us try to do hands-on demo on this. We'll try to work on this fraud detection using a set of transaction related credit card features. We are going to build a model using logistic regression to predict whether or not that particular transaction is fraudulent. So this is the problem statement. Let us also import some libraries while this runtime gets ready. NumPy, we are going to use definitely. Uh, what else? Pandas, Matplotlib as well. Matplotlib, Seaborn as well. If you want to do some visualizations, univariant, bivariant analysis, you're going to use these libraries, Matplotlib and Seaborn. Let us run this. I think the runtime is now connected. I can just upload this data that we have just downloaded. Okay, I think it is taking a little while to load. Okay, because I think it's 144 MB. That is why it is going to take a little while. Let us import the other libraries as well. Whenever you're working in any problem statement in industry setting, it's always a best practice. And I've seen this kind of work culture for every data scientist, like 5 to 6 different data scientists that I work with in my team. All of them use this same method of working, wherein whatever library they are going to import, that library will be at the top in that notebook. It's not the case that later if I'm going to use some library, I can import it at that point of time. If you're doing that in a habit of just writing the code and just putting the libraries anywhere you want, in the end, ensure that you bring all the library at the top. Okay, that is going to help the deployment process or make it easier for you to deploy your models. That's why it's a best practice. Okay, now what all things we are going to use from sklearn dot linear model, we are going to uh, import our logistic regression. Logistic regression. I think I'm writing it. It should give recommendation by now. Let us see where exactly logistic regression is. Logistic regression. This is my logistic regression in sklearn linear model. Hmm. Let me just copy the name. It's not giving me recommendation. It should give me recommendation. Anyway, let us execute this. Invalid. Okay, I think I've written import in both the places. From this, import this. Okay, that was why it was not giving me recommendation. Silly mistake. Okay, now let us try to read the data first to understand what exactly do we have here. So pd dot read CSV. Here I'm going to pass I have not written V here. Here I'm going to pass the file path. I'm going to copy it from here and I'm going to put it over here. This is my data. I'm going to call it as my data frame. You can call it whatever you want. I'm calling it data frame because this is a heavy sized data. Despite that, it only took 2 seconds. I was expecting it to take a little more. Okay, this is the data that we have here. Now, this kind of feature that we have here, I'm going to explain you what exactly you're seeing right now on the screen. The first column that you have, this time column, it represents how much time has passed between the first transaction in the data set over a period of time. So this is just that calculation, the elapsed time for the transaction, given that you are comparing it with the first transaction. All of these other features that you're seeing, starting from V1, V2 until V28, these are your principal components. Let me write it down as well. So what I'm saying is that this time feature that you have, this is your time elapsed. Whereas if I talk about V1 to V28, these features that you're seeing, these are your principal component analysis features. These you have obtained after applying PCA on your data. PCA is used for dimensionality reduction. You would not have come across principal component analysis until this point. That is because it is part of unsupervised machine learning. You're going to understand what is PCA, why do you use it, how do you use it, all of that you're going to understand. But right now, it's important to understand just that we have done something on the data to reduce the number of features. You can understand if we have applied something to reduce the number of features in our data, even after reducing that, we have still 28 or 30 features in our data, which means that in the original data, we would be having probably 100 or 200 features. These many number of features in your data is not good for your model. That is why you have to use some technique to reduce the dimension or reduce the number of features in your data. That is where principal component analysis comes into picture. Although this is a separate topic, we are not going to talk about that, but just because it is part of this data, that is why we spoke about it. Let me see if I can just change this. Yes, I think this is much better. Let me just put it over here. Data, metadata. Okay, now let us talk about the other features that we have here. We have the amount for a particular data point. What is the total amount that has been spent? So this one row corresponds to one single transaction. For example, if I'm making a transaction, this is my data point and I have spent this much money. So this is my transaction amount. Let me write it over here. Transaction. This amount is your transaction amount. Okay. Then what do we have? Class. The last feature that we have is class. This class is nothing but a prediction, or you can say fraud, not fraud, flag. It can only take two values, 0 or 1. If the transaction is a fraud transaction, it will be 1. If the transaction is a not fraud transaction, it will be 0. These are the values that it can take, and this is what you can understand from this data. Okay. Anyone has any question on the data? I understand if you're not able to make any sense of V1 till V28 values, but that is totally fine. You can skip that for now. We are going to use logistic regression on this data and train our model to predict for a given data point if it is fraudulent or not fraudulent transaction. Let us use logistic regression for that. Already the data has been converted, the pre-processing has been done. So starting off with, what you can do, you can just do basic understanding of how many records we have in the data. So we have 284,000 data points, some odd numbers, and 31 columns in total. Next, probably you want to take a look at the column names. You can do that over here. If you want to understand the data types as well, you can do that using this D types. We can see all of that is in the appropriate format. Now, next, if you want to get a 5 point summary, you can do that as well. So df.describe, and I'm going to get a statistical summary for all the numerical type of data that I have. If there is a categorical data, then I'll have to do a include is equal to object. I'll have to pass that as a parameter inside this to get the statistical summary for that kind of variable. Next, if you want to get the information, basically this is going to combine the count of null and non-null along with the data type as well. So you can do this as well. Using this, you can understand if certain columns in your data have null values or not, or what is the data type as well. All of that you can see in just one place. For that, you can use .info. Then what more we have? We already have seen. Let us check if there are null values. So here I can see that we do not have any null values. There's no null value, so we don't need to perform any kind of null imputation. You can check for outlier when you are going to do univariate or bivariant analysis, where you're going to plot your box and whisker plot. You can check for outlier there. That is part of pre-processing that you're going to do. You can plot different kind of graph as well, for example, bar graph and all of that. Let us do that. Let us do some visualization as well. Visualization. At least try to understand how the target variable is distributed. Visualization. So let us do that. In my data, so I have this class column, which is my target variable. I want to understand or get a value count. Uh, okay, I think I've missed out on this. Now, what we can see here is that for this class, we have 284,315 data points, but for this class, we have very less number of data points. Now, what this class 1 corresponds to? Class 1 here corresponds to fraud transaction. It is clear that fraud transactions are rare. They are not going to happen very frequently. That is why always whenever you're trying to work on fraud detection, the data distribution will be skewed, very heavily skewed towards one class. So in this type of situation, we call this as a minority class and we call this as a majority class. This is the imbalanced data problem that we are going to talk about. How do we deal with that in this session, in the next session? Probably will not be able to start today, but we are going to talk about this problem, and this is a very common problem in classification kind of problem statement. In logistic, this, how do we solve it? We have different techniques. We are going to talk about all of that, but right now we are not going to solve that because we'll have to cover that topic first before solving this problem statement. Now, if you want to plot it, you can use matplotlib. So I can use dot plot. And what do I want to plot? I want to plot a bar graph. So you can do that. If you don't want to see this kind of weird thing coming, you can do plt.show and you will get rid of that and you will just get the visualization. Here we can see this is a minority class and this is a majority class. Why this is a problem? Because my model does not have that many data points to learn the patterns of this class. How will it do the prediction if it has not been trained on sufficient number of data points to understand the hidden pattern in this kind of transaction, right? So it becomes difficult for a model to predict minority class. That is why we need to deal with this problem. We'll talk about that in detail. So let's just leave it over here. You can check the percentage, what percentage of data point fall here, what percentage fall here by just changing the here. You just have to change something. You'll get the percentage value as well. All of that you can do in your own time. Now, can we handle it by scaling? Milind, scaling is not going to help you with imbalanced data set. Scaling does not produce new data points. It just changes the distribution of your existing data. Your data point, for example, earlier it was having a value of 3, later it will get, that value will get modified to 0.00 something like that. But you're not going to make new data points by scaling. Scaling is not for creating new data points. So You cannot solve this using scaling. Okay. Yes. Now, first thing that I have to do here is I have to get rid of I have to separate my uh, independent variables and dependent variables. If I want to do the prediction, I'll have to separate that. How I can do that? So this is my data frame. So I can say that from my data frame, wherever the class variable is 1, okay, what kind of data that represents? It represents fraud type of data. So I can just give this. Now, a normal transaction will be exactly different to this. So in my data frame, wherever the class variable is 0, that is my normal transaction. I think I do not need this. So I'll just leave it. This is how you can separate your fraud transaction and your normal transaction, right? By using this class or the target variable. Let us run that. Okay. Now, what you can do if you want to get a statistical summary of certain columns, you can do that as well. So for example, in this fraud, let us try to see what do we have here. Fraud. So here we have class 1 related data points, all the data points where the class was 1. I think this is not the data frame. If I want to get the data frame corresponding to that, I'll have to wrap it with this, and let us do the same for this, because I should not be getting just the flag. I should be getting the entire data point corresponding to class is equal to 1. So let us see. Yes, now it is working. In this fraud data frame, whatever rows or records you are seeing, all of that corresponds to fraudulent, sorry, this is one, yes, fraudulent transaction. Whereas all the data points in your normal data frame corresponds to a normal transaction. If you want to check how many data points we have here, you can see this much. And if you want to check here, you can do that, but it will align with this count. So initially, when we did this, let me just copy this and let me just run it over here. If you do not remember the numbers that we got here, this exactly should match. So 492 data points we have in this data frame because we have separated all the records wherever the class was 1 and 0, right? So this is going to definitely match, right? Now, now that we have separated the fraud and not fraud transaction, you can do different level of analysis on these data sets to understand what exactly determines a fraudulent transaction versus what determines a non-fraudulent transaction. You can do all that level of analysis. That is totally up to you. You can also do a sampling wherein you can generate more number of random samples so that this is not a minority class, because that is going to cause a problem for your model. All of those techniques to deal with imbalanced problem we are going to see, and we are going to apply that as well, but not today, because today it's just a basic logistic regression class. That is why we are just going to build a model on top of that. Now, okay, let us develop a model. So now we are going to do model development. Model development. In this model development, okay, I think I've not taken text here. Okay, I think we already have imported logistic regression. So let me just initialize the class logistic regression. How can we initialize? Just by calling that, and we can store it in a variable. I'm going to call it model. You can call it anything you want, and then you can start building your model. Before that, I'll have to separate my target variable and separate my independent variable and dependent variable, right? So how do we denote that? Using capital X and small y. So whatever my data is, if I drop my column, which column I have to drop? So I can just give my target variable. If I drop this column, access is equal to 1 because I want to drop all the records. Row wise deletion I have to do. That is why I'm using this. This will become my set of independent variables because I'm getting rid of the target variable because this is the only dependent variable that we have. Now, if I want to get the dependent variable, what I have to do? I have to just take this. This is my dependent variable. I can assign it in this. That's it. We have now separated independent and dependent variable. You can take a look at the shape and just for verification, you can understand how much data point you have over here. Now, now we're going to do train test split, but I think we have not imported the library using which we do the train test split. So let us do that over here, or let us go back to the top and let us import all the library over there only. So here, one more library now I need. So I'm going to from sklearn dot model selection import train test split. Using this, I'm going to split my train and test. I also need to evaluate the performance of the model that I have built. So for that, I'm going to import another metric from sklearn dot metrics. The way we imported mean, absolute error, mean squared error, and all of that lies in this library only. Here we have something which is called as accuracy score. Using this, we can evaluate the performance of a classification type of problem statement. I will talk about the formula for this, but right now we are just going to use it. And I think in the last class, when I just touched upon confusion matrix, I spoke about the accuracy, but not in detail. So anyway, we are going to cover that. So just for now, understand that this is used to evaluate the performance of a classification type of problem statement. A very basic evaluation technique. We have advanced evaluation techniques as well, more developed one, for example, precision, recall, F1 score, and all of that, which we are going to talk in detail. But let us come back over here. Now I'm going to use my train test split. I'm going to pass my X, Y, my test size. I can give 20%, 30%. I'm going to give 20% and random state to have the same reproducibility of my output. Okay, now I have to just unpack this. So let us do that. So here I'm going to get my X train, my X test, Y train, and Y test. Let us run that. We have done train test splitting as well. Now that we already have initialized this model, what I can do, I can use model.fit to train my model. What do I have to pass here? X train and Y train. Now that I have trained my model, it is going to take a little bit of time because I have a little higher number of data points. Yes, now we have trained this. There are some warnings which right now we can just ignore. Later on, we'll talk about this as well, how we can solve this. We can change the solver variable. I have just initialized this in a default parameter setting. I've taken the default parameters which are provided in sklearn logistic regression, but you can change this. So I think the warning is on maximum iteration. So you can change these values and you'll be able to get rid of that. We are going to talk about that in hyperparameter tuning for this. We are going to cover that as well. Now that we have trained our model, we need to get the prediction. How? Model.predict. On what? You can get a prediction on trained data as well, but usually we can do it on test data. Now I can store it in my prediction, or rather I can just give it vibrate. Just the naming convention depends on you. Now that I've got the prediction as well, if I have to evaluate the accuracy, I'm going to use accuracy score. And what do I have to pass here? Actual value, which is my Y test, and the predicted value. That's it. Now let us try to see. You can see here what is the accuracy that we have got here. 99% accurate. 99.8, which means that it is nearly classifying all the data points correctly. Only few mistakes it is doing in classification. So it's a very good model that we have built. There is a reason for that. Why, despite having this imbalanced problem, it was able to give this much accuracy. There's a reason for that. We'll talk about that at some point, definitely. While we'll cover all of these topics, we'll talk about that as well. Okay, but this is how you build a logistic regression model. What changed between linear and logistic? You are still using sklearn library. You are still separating independent and dependent variable. You are still splitting your data in train and test. What changed is how you evaluate the performance of your model. There, you used to use mean squared error, mean absolute error, all of those things, but here you use different metrics to evaluate the performance of your model, right? And also, the prediction that you get here is in form of probability value. That is not the case for linear regression, right? So these things are some of the small changes that you would see between linear and logistic. As we move ahead, I'm going to talk about more differences between linear and logistic. But overall, this is a basic, simple logistic regression that we have built. Let us take a break of 5 minutes and then assemble back. And we are going to start with confusion matrix, which is a very, very crucial topic. I'll try to explain with examples as well to help you easily understand and get familiar with the terminologies that we use in day to day life. And you're going to definitely come across this very, very often in industry. Now we are going to start a very important topic, which is confusion matrix. And using this confusion matrix, we are going to derive the evaluation matrix. So confusion matrix. Using this, we will derive precision, precision, recall, F1 score, and these are your evaluation metrics. Evaluation metrics in any classification type of problem statement. This is not specific to just logistic. The way when I was telling you about the evaluation metrics for linear regression, linear regression, when we spoke about mean squared error, mean absolute error, mean absolute percentage error, R2 score, R2 score, right? All of these were the different evaluation techniques, adjusted R2 score as well. Why to leave that one behind? Adjusted R2 score. These evaluation metrics are not just for linear regression, but it is applicable and it is useful for any type of regression task that you're trying to solve. Be it you're using decision tree algorithm, still you can use these metrics to evaluate the performance. If you're using random forest algorithm, still to solve a regression type of problem statement, still you can use these metrics to evaluate the performance of your model. Any algorithm, irrespective of that, if the kind of problem that you're solving is regression, you can use these evaluation metrics. Same goes for classification type of problem statement. Any classification problem statement you're trying to solve, you can use these metrics to evaluate how good or bad your model is performing. That is why we call them as evaluation metrics. We can derive that from confusion matrix. So let us talk about what exactly is confusion matrix. Confusion matrix tells you whether your model, how many wrong or right prediction your model is giving. So all in all, confusion matrix will give you that number. Matrix tells you about wrong and wrong and right predictions. Predictions. In the last class, I think we already took an example wherein we were trying to build a spam classifier. Spam classifier. In that spam classifier, I had taken a 2 by 2 confusion matrix. And this 2 by 2 confusion matrix, why 2 by 2? Because spam classifier can only have two output or two target, right? What are those? Spam or not spam. It cannot give any other prediction or any other output, right? So that is why we have 2 by 2 confusion matrix. If I'm doing a prediction for multi-class classification, in that case, the output or the confusion matrix will look different. The dimension of the confusion matrix is going to change in that case. So this is only applicable for binary class classification. Now let us try to build that here. So spam, not spam. Here we have spam and not spam again. Spam, not spam, not spam. Now, As in the last example as well, I think I had taken 1000, let us say that I have 1000 data points using which I'm trying to build my spam classifier. Out of those 1000 data points, let us say 300, 500, 800, and then we have 150 and 50, 950,000, right? What this represents, if you see numbers like this populated in a confusion matrix, how do you get inference from this? To understand this, first thing that, how do you read it? So what this is saying that is that actual uh, the actual data point was actually a spam email, and my model was able to classify it as spam. How many such instances we had? 300. Whereas we had 500 instances or 500 data points where those data points were not spam, and my model also was able to predict it as not spam, which means that if I have to calculate the accuracy, how I can get the accuracy? 300 plus 500, 500 divided by, yes, 1000. So this will be my 800 divided by 1000. 100 percentage. No, no, this is not 100% accurate. 100% accurate would have only been when all of my data points would fall in these green colored boxes. None of the data points would fall in these boxes. Then only it will be 100% accurate. Right now, this is not 100% accurate. Yes. So this is my 80% accurate. Now, if I have to talk about the error that my model is doing in prediction, these are my errors. These are the mistakes that my model is doing when it is trying to give the prediction. What is happening here is that actually that particular data point was not a spam email, but my model predicted it as spam. How many such data points we had? 150, this particular box. Whereas this particular 50 box here, actually those data points corresponded to spam email, but my model said that it's not a spam. So this is my error that my model is making. There is certain naming convention for this type of error, so we call this as type 1 error, and we call this as type 2 error. We are going to talk about that later, not right now, but just that I wanted to introduce the terminology. Now you are going to tell me, I'm going to take an example and you're going to tell me this accuracy is nothing but the same accuracy score that we imported from sklearn. This is that. This is the formula using which you calculate it. I'll also tell you why exactly this accuracy is not a good measure. So we'll talk about that as well. And that is why we had to move towards precision recall F1 score to evaluate the performance of our models, because this accuracy is not always a good measure of the performance of your model. We'll talk about the why part later. I want to give an example so that you can tell me what did you understand from confusion matrix and how do you read a confusion matrix. So let us say that I, as a data scientist, have built a fraud detection machine learning algorithm. I've used machine learning algorithm to build a fraud classifier. Fraud transaction, not fraud transaction, not fraud. Fraud transaction, not fraud transaction. So let us say that I had transaction data points for 2000 customers. Out of that 2000, the confusion matrix looks something like this. So 50, 50, 800. I think it will be 1100. Let us try to understand and read this confusion matrix so that we are able to relate with these things very easily. What we are saying is that out of, so there were 50 transactions which were actually fraud, and my model also predicted it as fraud, which means that this is my correct classification, right? Correct classification that my model is doing. Now, I had 50 transactions which were actually not fraud, and my model also predicted it as not fraud, which means that this is also correct prediction. Now, coming to here, this block. In my data, I had 800 not fraud transactions, but my model predicted it as fraudulent transaction, 800 data points, which means that I am going to call 800 customers and I'm going to bother them saying that, hey, I think there's a suspicious activity, fraudulent transaction is happening, even though the transaction was not fraud. This is going to bring a very bad customer experience. This is not good, right? And anyway, if a machine learning model is making a mistake, it can never be good. The more the number or the intensity of the mistake is, the bad the model is going to be bad on that scale. 1100 1100 data points or the transactions that I had was fraudulent transactions, but my model predicted it as not fraud. This is also not good. In real world example, this is also bad, because you are saying that I am going to misclassify fraud transactions, which means that I'm going to pass those transactions. If you are not able to block the transactions which are fraudulent, then what is the use of having a fraud detection in the first place, right? You are not actually going to use it if your model is giving wrong predictions, right? So this is also not good. Now, to calculate the accuracy, what you have to do, how many correct predictions your model has made? Can anyone tell me how many correct prediction my model has made? If you're not able to see, okay, okay. Anyone else? So if I have to calculate the accuracy, in the numerator, I'm going to have the correct number of correct predictions, number of correct predictions divided by, in the denominator, I'm going to have total number of data points or total number of predictions. Total number of predictions. Exactly. Absolutely. Sahil, Milan, Shubhi, Vasudevan. Absolutely. So here I had 50 plus 50 data points where my model has made correct predictions, these green boxes. And in denominator, I'm going to put in the total number of predictions. Total number of predictions were made for how many data points? 2000 data points, right? So that is what I'm going to put over here. Now, if you calculate this, it will be 100 divided by 2000 and it will come as 5%. This is what Millen and Thalish has given the calculation for. Now, if you're not able to just look at the confusion matrix and understand if the model is good or bad, if you calculate accuracy and you get this value, just by using this as well, you can say that this is a bad model, right? So using that also, you will be able to tell. Now, let us familiarize ourselves with some common terminologies that we have in confusion matrix, and we'll try to understand what it means. So here we have, in this side, we put actual values on this side, and on this side, we put predicted values. Predicted values. Let us say I'll take the fraud, not fraud only. Fraud, not fraud, not fraud. Here also, fraud, not fraud. True positive, true negative, false positive, false negative. And you're going to hear these four terms again and again and again across any kind of classification problem, not just limited to logistic, but also decision tree, random forest. If you are going to use those algorithms to solve classification kind of problem, you're going to hear these four terms again and again and again. So familiarize yourself with these terms now. If there's confusion, just slow down and listen and try to understand and ask me to repeat that part. I'm going to do that. But it's important to be clear on what these terms represent. First of all, before we understand these terms, let us understand positive and negative class. Positive and negative class. class. Let me go back to the PPT, and I think using that, I'll be able to give you one reference or one example. In this example, what we have strawberry and we have apple. Strawberry is taken as positive class, whereas apple is, where is the apple? Let me see. Okay. Here, apple is taken as a negative class. Okay. So I'll just initially take this one example, strawberry and apple. Strawberry and apple. In the PPT that we have, this has been taken as a positive class, whereas this has been taken as a negative class. If I'm trying to predict for a given set of features for fruits, I'm trying to predict if it belongs to strawberry or apple class. What kind of classification problem it is? Binary or multi-class? Quickly, binary or multi-class? Binary? Absolutely, binary. Now, how do we label any class as a positive or negative class? Class is what? Class or label? Class or label is nothing but the output or target, something that you're trying to predict. We call it as class or label. Now, how do you assign or how do you say for a given class if it is a positive class or a negative class? In the PPT, we can see strawberry has been called out as a positive class, whereas apple has been called out as negative class. There is no hard and fast method using which you can label a class as positive or negative. Okay. And specifically in the examples where it does not make sense to label a class as positive negative, you can just manually go ahead and decide that, okay, this is my positive class, this is my negative class. If you want, you can call this as negative class, you can call this as positive class, doesn't matter. It's up to you. There's no hard and fast rule to determine positive or negative class. Okay. But there are certain things using which people usually go ahead and classify or label the classes as positive or negative. So, for example, if I'm trying to build a cancer prediction model using supervised machine learning, in that case, the output that I'm going to have, it will be cancer, no cancer, no cancer. It's a binary class classification problem statement. So I'll have positive and negative class. When you are more concerned about predicting this class, you don't care if this prediction comes wrong or right, you don't care about that, but you care about this prediction. If a person, if a patient or a person has cancer, it should not be mispredicted or misclassified, it should be correctly identified. This is what you are more concerned about in your problem statement, right? In that case, you can label it as positive class, and something which you don't care much about, you can call it as a negative class. This is one way of identifying positive and negative class. If I talk about fraud transaction or not transaction, fraud detection, machine learning algorithm, detection ML algorithm, the output that you're going to have, it will be either fraud or not fraud. Now, you don't care if your model makes wrong predictions about a not fraud transaction, but you very much care and you are more concerned about the prediction for fraud transactions. Fraud transactions should not be misclassified because you want to detect the fraud transactions as early as possible so that you can block the transaction and you can prevent the loss of financial money, right? Loss of revenue. That is why this is more crucial for your model to not misclassify. That is where you can go ahead and call it as a positive class and you can call it as your negative class. Anything which in your problem statement you are more concerned about that your model should get it right, that acts as a positive class for you, whereas the other thing that you have acts as a negative class. This is general one way using which people classify positive negative. Otherwise there's no hard and fast rule. Even if you're solving fraud detection, you want to call this as your positive class, you can do that. You want to call this as your negative class, you can do that. No one is going to stop you. So there's no hard and fast rule, just some standard industry practice which people use. Now let us talk about this true positive, false positive, true negative, false negative. True positive. Now that we know positive and negative classes, it will become very easy for you to understand. True negative, false positive, false negative. First of all, let us talk about true positive. We are going to slowly understand it. I'm not going to rush into it because I don't want anyone to miss out on these topics. It's very important. True positive. What this box represents is the number of instances or the number of predictions which the model has got correct, right? So here, if I talk about spam, I had spam here. Actually, the data point was for a spam and the model was able to predict it also as a spam. So it's a correct prediction. And let us say I'm doing a spam classification. The output can only take these two values, spam or not spam. I am more concerned about spam prediction. So I'm going to call this as my positive class and I'm going to call this as my negative class. This is what I have decided. Okay. So let me just put the other value here as well, not spam. Okay. What true positive represents is that how many instances in your prediction you are able to correctly identify. In instances of what? Positive class. So positive class, positive class. How many correct predictions your model has done for positive class? That is your true positive. Truly predicting a positive class, that is your true positive. If I talk about true negative, you are making a correct prediction. That is why we are calling it true. And what you are predicting is a negative class. Not spam is the prediction, right? And not spam is which class? It's a negative class. So the prediction that you're doing is correct. That is why we are calling it true. But the output that you have is a negative class. That is why it is true negative. Truly predicting the negative class, truly predicting the positive class. This first term indicates that your model has done the correct prediction, and the second term indicates which class is your output. Is it a positive class or is it a negative class? Now, we spoke about true negative as well. True negative. So, how you can just in simple, you can just say it as truly predicting, predicting positive class. So your model is making correct prediction for positive class. Spam is which class? Positive class. Correct prediction for positive class. Whereas true negative means that your model is making correct prediction, but the prediction is for negative class. Negative class. That is your true negative. Now, the combination of true positive and true negative. This tells you how many correct predictions your model has given. Correct predictions. Out of all the data points that you have for which you are trying to get the prediction from your model, how many of those are your correct predictions? The sum of true positive and true negative. Now let us talk about false positive and false negative. False positive. I think by now you would have understood this as well. Falsely predicting, falsely predicting positive class, which means that my model is giving a wrong prediction. Falsely means wrong prediction, and the prediction is a positive class, which means that what is my positive class here? Spam. If I'm saying that my model has given spam as output and it's a false prediction, it means that the actual value would have been not spam, right? So if you look at the false nature, categorical in nature. Categorical means that it can only take certain distinct values or certain unique values. Probably, for example, if I have to give you positive and negative class, positive and negative class. Let me go back to the PPT, and I think using that I'll be able to give you one reference or one example. In this example, what we have strawberry and we have apple. Strawberry is taken as positive class, whereas apple is, where is the apple? Let me see. Okay. Here, apple is taken as a negative class. Okay, so I'll just initially take this one example, strawberry and apple. Strawberry and apple. In the PPT that we have, this has been taken as a positive class, whereas this has been taken as a negative class. If I'm trying to predict for a given set of features for fruits, I'm trying to predict if it belongs to strawberry or apple class. What kind of classification problem it is? Binary or multi-class? Quickly, binary or multi-class? Binary? Absolutely, binary. Now, how do we label any class as a positive or negative class? Class is what? Class or label? Class or label is nothing but the output or target, something that you're trying to predict. We call it as class or label. Now, how do you assign or how do you say for a given class if it is a positive class or a negative class? In the PPT, we can see strawberry has been called out as a positive class, whereas apple has been called out as negative class. There is no hard and fast method using which you can label a class as positive or negative. Okay, and specifically in the examples where it does not make sense to label a class as positive negative, you can just manually go ahead and decide that, okay, this is my positive class, this is my negative class. If you want, you can call this as negative class, you can call this as positive class, doesn't matter. It's up to you. There's no hard and fast rule to determine positive or negative class. Okay, but there are certain things using which people usually go ahead and classify or label the classes as positive or negative. So, for example, if I'm trying to build a cancer prediction model using supervised machine learning, in that case, the output that I'm going to have, it will be cancer, no cancer, no cancer. It's a binary class classification problem statement, so I'll have positive and negative class. When you are more concerned about predicting this class, you don't care if this prediction comes wrong or right, you don't care about that, but you care about this prediction. If a person, if a patient or a person has cancer, it should not be mispredicted or misclassified, it should be correctly identified. This is what you are more concerned about in your problem statement, right? In that case, you can label it as positive class, and something which you don't care much about, you can call it as a negative class. This is one way of identifying positive and negative class. If I talk about fraud transaction, or not transaction, fraud detection machine learning algorithm, detection ML algorithm, the output that you're going to have, it will be either fraud or not fraud. Now, you don't care if your model makes wrong predictions about a not fraud transaction, but you very much care and you are more concerned about the prediction for fraud transactions. Fraud transactions should not be misclassified because you want to detect the fraud transactions as early as possible so that you can block the transaction and you can prevent the loss of financial money, right? Loss of revenue. That is why this is more crucial for your model to not misclassify. That is where you can go ahead and call it as a positive class, and you can call it as your negative class. Anything which in your problem statement you are more concerned about that your model should get it right, that acts as a positive class for you, whereas the other thing that you have acts as a negative class. This is general one way using which people classify positive negative. Otherwise, there's no hard and fast rule. Even if you're solving fraud detection, you want to call this as your positive class, you can do that. You want to call this as your negative class, you can do that. No one is going to stop you. So there's no hard and fast rule, just some standard industry practice which people use. Now let us talk about this true positive, true negative, false negative. True positive. Now that we know positive and negative classes, it will become very easy for you to understand. True negative, false positive, false negative. First of all, let us talk about true positive. We are going to slowly understand it. I'm not going to rush into it because I don't want anyone to miss out on these topics. It's very important. True positive. What this box represents is the number of instances or the number of predictions which the model has got correct, right? So here, if I talk about spam, I had spam here. Actually, the data point was for a spam and the model was able to predict it also as a spam. So it's a correct prediction. And let us say I'm doing a spam classification. The output can only take these two values, spam or not spam. I am more concerned about spam prediction. So I'm going to call this as my positive class and I'm going to call this as my negative class. This is what I have decided. Okay. So let me just put the other value here as well, not spam. Okay. What true positive represents is that how many instances in your prediction you are able to correctly identify. In instances of what? Positive class. So positive class, positive class. How many correct predictions your model has done for positive class? That is your true positive. Truly predicting a positive class, that is your true positive. If I talk about true negative, you are making a correct prediction. That is why we are calling it true. And what you are predicting is a negative class. Not spam is the prediction, right? And not spam is which class? It's a negative class. So the prediction that you're doing is correct. That is why we are calling it true. But the output that you have is a negative class. That is why it is true negative. Truly predicting the negative class, truly predicting the positive class. This first term indicates that your model has done the correct prediction, and the second term indicates which class is your output. Is it a positive class or is it a negative class? Now, we spoke about true negative as well. True negative. So, how you can just in simple, you can just say it as truly predicting, predicting positive class. So your model is making correct prediction for positive class. Spam is which class? Positive class. Correct prediction for positive class. Whereas true negative means that your model is making correct prediction, but the prediction is for negative class. Negative class. That is your true negative. Now, the combination of true positive and true negative. This tells you how many correct predictions your model has given. Correct predictions. Out of all the data points that you have for which you are trying to get the prediction from your model, how many of those are your correct predictions? The sum of true positive and true negative. Now let us talk about false positive and false negative. False positive. I think by now you would have understood this as well. Falsely predicting, falsely predicting positive class, which means that my model is giving a wrong prediction. Falsely means wrong prediction, and the prediction is a positive class, which means that what is my positive class here? Spam. If I'm saying that my model has given spam as output and it's a false prediction, it means that the actual value would have been not spam, right? So if you look at the false positive, actual value was not spam and the model has said it as spam. So this is how you can trace it back, not spam to spam. This is the kind of mistake that your model is making in false positive. If I talk about false negative, falsely predicting, predicting negative class, negative class. If you have to understand where it would lie in your confusion matrix, how you can trace it, I know that my model is giving prediction as a negative class. What is my negative class? Not spam is my negative class, which means that my model is giving this as the prediction. And if I'm saying that it's a false prediction, which means that the actual value would be exactly opposite of this. So the actual value would be spam. So in your confusion matrix, here, spam to not spam. This is your actual value. This is your predicted value, right? So this is your false negative, spam, not spam. This is how you can easily identify and relate these terminologies in your confusion matrix. Anyone has any doubt on this confusion matrix? The terminology, at least false positive, false negative, true positive, true negative. We'll talk about type 1 error, type 2 error, and all of that. No? Okay, all right. Great.
Hey there, we hope you're enjoying our logistic regression bootcamp. If you are thinking about stepping into the world of data science and becoming a data analyst, we've got the right plan for you. Our data science and AI program makes your job ready in just 5 months, offering lifetime placement assistance and 5 dedicated mentors with one-on-one guidance. And you know what? More than 4,500 students have already been placed, and you can be the next. This is your chance to build your career with Newton School. Just fill out the form in the description and make it your first step towards a successful career in data. Now let's carry on with logistic regression.
Let us and try to see we have here. Great. Here we all the read thing. I have taken pause. If the strawberry model print as strawberry, I think that strawberry is my positive class, which means that my model is giving correct prediction and it is predicting positive class. So true positive. False negative means that my model is predicting a negative class and it's a false prediction. So for strawberry, it is predicting as apple. So it's a false negative. Falsely predicting a negative class. That is your false negative. Now, false positive, falsely predicting a positive class. What is my positive class? So my model is giving strawberry as a prediction. Strawberry, I have already said that this is my positive class. But the actual value was apple and my model predicted it as a strawberry. So clearly this is a mistake and this is a false prediction. And the prediction is a positive class. That is why this is a false positive. And the last one that we have in confusion matrix is true negative. True means that my model is giving correct prediction. Negative means that it is predicting negative class. What is my negative class in this example? Apple. So it is predicting apple as an apple. So that is a correct prediction for a negative class that I have in my example. Now, let us talk about precision, recall, and F1 score. We will be able to cover precision, recall, and F1 score today. I think after that we may not be able to go beyond it. Specificity, city, and sensitivity, all of that is a very similar metric, but this is very important. ROC AUC curve, very very important. In classification type of problem statement, always you're going to plot this kind of curve to evaluate how good your model is performing compared to a random model. And every time I've seen this getting used. So this is important. And then we'll talk about imbalanced data, which is good. Let us now try to understand the evaluation matrix, which we are going to derive using confusion matrix itself. Everything that we have covered in confusion matrix will get used now. Evaluation, evaluation matrix, matrix. And this is common for all classification type of problem statement, not just specific to logistic regression. I'm repeating that again. First is precision, precision. You don't have to memorize the formula at any point of time. You don't have to remember, just you have to recall what precision is. You don't need to remember the formula for this. Recall and then F1 score. In some textbook, you're going to see this written as F beta score because this beta value is something which changes basis the change in the formula. So in some cases it will be taken as 0. 0.5, in some cases this beta will be taken as 1, something like that. So it will become F 0.5 score, F1 score, so on and so forth. But standard textbook, you will find F1 score only. This is most commonly used, but there are different variations of this as well. We'll start with precision. Precision. In precision, we are trying to understand how many, what is the correct prediction that my model is doing. So the formula for precision is precision. Using the formula, I'll help you understand how to define this precision. True positive divided by true positive plus false positive. Let me draw the confusion matrix. I think it will help you relate with these terminologies as well. So this is my true positive, this is my true negative, false positive, and false negative. Okay, this was my confusion matrix. What precision says is that here, let me change my color. True positive divided by this. This is what we are doing here. What proportion of positive class we are able to correctly predict? So let me write here as well. This is my spam. This is my spam, not spam, not spam. This denominator here, this talks about denominator. This is what my total number of positive class prediction, positive class prediction. Because I'm saying spam is my positive class and here this is my prediction. This side is my prediction. Total number of positive class prediction is on the denominator and this talks about number of correct prediction for positive class, for positive class. Okay, because if you look at this particular part, this is incorrect prediction, right? So only this true positive is my correct prediction. What we are doing using this precision matrix is that we are trying to understand out of all the prediction that my model has given for a positive class, how many of those predictions are actually correct. That is what we are trying to understand using precision. Let us talk about the second evaluation technique, which is my recall. Recall. Very similar to precision, but the way we interpret recall is a little different, and the formula obviously is different. Recall. The formula for this is, and you don't need to remember that, true positive divided by true positive plus false negative. Drawing a confusion matrix is going to simplify this process for you. Always use this to understand this better. True positive, true negative, false positive, false negative. Spam, not spam, spam, not spam, not spam. What we are actually calculating in recall, let us see that. True positive divided by what we are dividing it with, true positive plus false negative. This entire sum is on my denominator. What this represents here, actual positive class values, and here we are talking about the correct number of correct positive class predictions. Positive class predictions. I'll take an example to help you understand precision and recall better. So I think that is going to help you. So let us draw a confusion matrix and give some numbers. So this is my confusion matrix. Spam, not spam, same classic example. Spam, not spam. I'll take an example to simplify precision and recall for you. Spam, not spam. Let us take the same 1000 email example. Let us say we have data point corresponding to 1000 emails, and I'm trying to get my model to predict the whether it is a spam email or not spam email on this data set. So here, let us say 300, same values I'm going to take 500, 150, and 50. If I have to calculate precision, let us try to first of all calculate precision over here. Precision. Precision will be my true positive value, this value. I'll have to divide it with my this entire this entire set 300 plus 150. This is my precision. You can just do the calculation. 300 by 450. You can calculate the percentage for this. If I have to calculate the recall will be again here true positive, and we have to divide it by the sum of this 300 plus 50. So it will become 300 divided by 350. You can do the calculation for percentage value, and what we are trying to understand here is that we are trying to capture how many wrong predictions my model is making on positive classes compared to the negative classes. Everyone able to understand this formula? Any confusion on precision and recall? Anyone? We have seen this using confusion matrix. Clear? Clear? All right, amazing. Now let us try to understand this in terms of business sense. What this precision and recall is going to tell you. It is saying precision here is saying that I had 450, 300 plus 150 in my this data set where I have 1000 email. I have 450 instances where my model has predicted it as spam, but actually only 300 of those predictions are correct. Right? This is what I'm trying to say using this precision. Whereas if I have to understand recall, what we are saying is that I had 350 instances where actually the email was a spam email, but out of those 350 instances, only for 300 data points, my model was able to correctly classify it as spam. In some cases, it can happen that precision is an important evaluation criteria for you, whereas in some cases it can happen that recall is important for you to evaluate. It will depend on case to case. We are going to see some examples to understand in which case you should focus more on improving precision versus in which case you should focus more on improving recall. We are going to take example, industry example, for example, spam classification or cancer prediction or those kind of examples. We'll see which one you should prioritize to improve when you're building a classification model. We'll see that example. Before that, let us finish this evaluation metric. The last one that we have is F1 score, right? What exactly F1 score is going to tell you? Let me just change the color. Anyone remembers the formula for harmonic mean? Anyone? You have already covered maths for machine learning, and you would have, I think, gone through with these mean, median, mode, averages, all of those. Harmonic mean, anyone? No? Okay. All right. What exactly F1 score is? Nothing but harmonic mean of precision and recall. Precision and recall. The formula for harmonic mean is AB divided by A plus B. Twice of AB divided by A plus B. All I have to do here is substitute this A and B with precision and recall, and you will get the formula for F1 score. Let us do that. The formula for F1 score is 2 times 2 times precision multiplied by recall divided by sum of precision and recall. This is how you can calculate F1 score. Nothing but harmonic mean of precision and recall. The question is why we needed another evaluation metric when we already had precision and recall. The reason is in some cases it can happen that you have to focus more on improving precision, whereas in some cases it can happen that you have to focus more on improving recall. But there can also be some overlapping cases where you have to focus on improving both precision and recall. So, for that reason, researchers came up with F1 score. F1 score. All of these evaluation metrics that we're trying to understand, in the end, the aim is to get better accuracy. The higher the value of precision recall, the better your model is, right? So, you have to improve these precision and recall to have a better model. For example, if I built a spam classifier and I'm getting precision value as 80%, precision is 80%, and in my spam classifier, I'm getting recall value as 70%. Now, let us say tomorrow my stakeholder comes in and says that I don't think we'll be able to publish this model in deployment because we have very less recall value. Now I know which metric I have to focus more on. I have to improve recall, right? I am clear on this objective. But there can be certain cases where you have to focus on improving both precision as well as recall. In that case, you can capture F1 score because F1 score is nothing but the harmonic mean of these two, and you can work on improving F1 score, right? So, this is how you can prioritize evaluation metric. Let me go back over here. I think I would need to put these formulas. Let me just put it in one place. Using the formula, I'll be able to help you understand how exactly do you understand, how exactly do you improve these evaluation metrics. First of all, precision. Precision. The formula for this that we had written was true positive, and in the denominator, we have true positive plus false positive. For recall, what was the formula? True positive divided by true positive plus false negative. Sorry, false positive. This is what we had for recall. Now, if I have to write for, sorry, I think here we had, let me just erase this. This will be my false negative. False negative. Let me just draw this box. True positive, true negative, false positive, and false negative. So it will be here false negative, and here will be false positive. Now, F1 score. 2 times your precision multiplied by recall divided by precision plus recall. Precision plus recall. If I'm saying that I want to improve precision in my model, this is more important evaluation metric for me in my model. My stakeholder said that I need better precision model, which means that I have to improve this. If I have to improve this, I have to reduce the number of false positive errors because true positive is the correct prediction, right? So I don't have to reduce this, but this false positive is my error. This is the mistake that my model is making. If I'm able to reduce the false positive, then automatically my precision is going to increase. Just by looking at this formula, you can easily derive this. To improve precision, you have to Reduce the instances where your model is making mistake on false positive. This mistake that your model is making, if you are able to reduce this mistake, automatically your precision will increase or improve. Whereas if someone comes and tells you that, hey, I need better recall in this model, you need to improve your recall, which means that they are trying to say is that focus on having less number of false negative error in your model. Improve your model by reducing the false negative cases. This error, this is your type 1 error. We'll talk about type 1, type 2, just a naming convention. Type 2 error. Okay, this is how you can understand. If I say that I need better precision, it means that I need less false positive mistakes in my model. If I'm saying that I need to improve my recall, it means that I need less false negative cases in my model. Whereas if your stakeholder says that I don't want both types of mistakes, I want to minimize false positive as well as false negative, both errors I want to minimize, then you're going to focus on F1 score. Is this clear? Yes. F1 score formula will be the same if beta is used in place of 1. Shubhi, F1 score formula is going to change if the beta value changes. If it is 0.5 or 0.1 or any other value, F1 score formula is going to change. There's a beta factor in the formula which is associated. So basis that this formula will change, but in industry always you're going to use F1 score because the other variant that we have that is not popular in machine learning algorithms. So always you will use F1. So beta is equal to 1 is default. You can read the default documentation for F1 score on sklearn. I think there will be documentation. Let me just see what all we have there. So sklearn F1 score. Probably in the parameter they would have taken beta is equal to 1. So I think they have not taken that parameter, but yeah, I think they have written the same kind of harmonic mean example formula over here. They have not taken that parameter. The default is 1. I don't know what they're doing here. They are solving it for multi-class and binary. So that's a different thing. I don't think they are using it over there. Let us go over here and see if we have the beta related example. Okay, where is F1 score? This is the F1 score that we have. Yeah, I think beta variable related formula you're not going to see because it's not used at all. So we'll skip that. No worries. In the implementation also, you'll be able to see how we capture F1 score, actual, predicted, all of that. We are going to see that example as well. We'll calculate. Today in the example, we only calculated accuracy score. And that accuracy score is nothing but the total number of correct predictions divided by total number of prediction that your model is giving. Whereas now that we have already understood precision recall and F1 score, we can evaluate the performance of this model using precision recall and F1 score as well. We can do that. If you want to read about confusion matrix, you can do that on the official sklearn library. On sklearn, we have the package using which we'll be able to import and get the value of true positive, true negative, false negative. Beta is a variable. So in F1 score, the value 1 is actually a value of beta. Originally in mathematics, F beta score exists. But in machine learning classification type of problem, we replace this beta with 1 and we call it as F1 score. But at some places, you will see F 0.5 score as well. In that just means that the beta value in this case is not 1, but it's 0.5. But we do not use these scores. These mathematical equations we do not use. We just use F1 score, which is the harmonic mean of precision and recall. You can read about this confusion matrix, but not required at all. But we are going to use this. We'll see for a problem statement that we'll solve. We'll get the confusion matrix. We'll try to understand the confusion matrix. Confusion matrix for a binary class classification is a lot simpler to understand compared to the confusion matrix for a multi-class classification problem statement. So here you can see the confusion matrix that we have. It is for a multi-class classification. Distinct target variable, is what we are trying to predict here. That is why we have 3 by 3 confusion matrix. I've seen the problem statements where we have even had 5 by 5 confusion matrix. It becomes a little difficult to interpret that kind of confusion matrix, but I think we'll solve a problem statement where we are going to have 5 by 5 or 4 by 4 confusion matrix, and we'll try to understand that as well. In these kind of confusion matrix, the terminology that we have just introduced, which is true positive, true negative, false negative, that will change slightly. The way you would understand true positive will be different compared to how we have understood for a 2 by 2 confusion matrix. But we'll cross that bridge when we'll come there.
Let us assume that I have a data. In my data, my x1, this is some feature that I'm taking. I have another feature which is my x2, another feature x3. I have three features in my data. These are what? These are my independent variables. I have a target variable, something that I want my model to predict. I have a historical value for this. So, for example, I have data points, and corresponding to those data points, I have this y value. But I want to create a model that can predict this value for me going forward in the future. For unseen data, this prediction should happen. So, I'm going to build a model. And once I built my model, I am going to get the prediction. Let us say that the prediction is y hat. The notation that we use to represent the prediction is y hat. So I have written it like that. Now let us just take y and y hat. When we are talking about classification type of problem statement, let us assume that this example was for spam classifier. Now, in my original data, the actual output can only either be spam or not spam, right? It cannot take any other value. So original output, I'm going to replace spam with 1 and not spam with 0. You can convert it into binary number. So I'm going to do that. So let me get rid of this line. Okay. So let us say that here we had 1, 0, 0, 0, 1, 0. These are the actual output data points that I have in my data already with me. And when I built a model, when I did a model.fit and I did model.predict, in the prediction of classification type of problem statement, you are going to get probability value. So let us say that for this particular data point, for corresponding to that particular data point, the prediction, so prediction was, for example, I'm just assuming prediction was zero point 0.8, zero point 0.6, zero point 0.2, zero point 0.4, zero point 0.3, and 1. These were the predictions that my model has given after I applied logistic regression on the data that I had. Now, what I have to do, I have to convert that into a class label, because if you would look at the actual output was an absolute number, 1 or 0. But in the prediction that I have got, it is not an absolute number, but it is rather a floating point number. I need to convert that into class label. So, how I can do that? I can write a rule. So, for example, I can say if y hat is greater than 0.5, greater than zero point 0.5, then label is equal to, label or output or class is equal to, I'll say it's a spam. Else label is equal to, label is equal to 0. This is the rule that I'm going to use to classify or convert this prediction probability into a label of a class. Let us do that. And this we are doing at, so this is at threshold is equal to 0.5. So I think when I had shown you the S-shaped curve with an example of age versus if you can vote or not, there also we were taking the threshold value of 0.5, above which we were saying that people can vote, below people cannot vote. So this was the threshold that we were doing, taking, kind of it was acting as a decision boundary to get the final prediction. Same thing we are doing over here. Now, if this rule has to get applied, what will be the final class label here in this case? This value, is it greater than 0.5? Yes. Output will be 1. Is it greater than 0.5? Yes, 1. Is it greater than 0.5? No. Is it greater than 0.5? No. Greater than 0.5? No. Greater than 0.5? Yes. So now what you have to do to check how accurate your model is, you have to compare this original actual ground truth output value with this target predicted value. So this is what your model has predicted, and you have to compare this. Now let us try to see is your major concern. So you would call spam as your positive class and not spam as your negative class. So basis that, you have to tell me, given that this is the actual value, this is the predicted value, how many true positives do we have here? In how many of these cases the model predicted, the model prediction was correct and the prediction was a positive class? That is your true positive. Quickly, anyone? You just have to compare this with this. That's it. One, okay? Everyone is right. We only have one case of true positive, first one. Now, true negative, in how many cases the prediction that model has done was correct prediction, but the prediction that it has given is a negative class, which is not spam. So only you have to look at not spam prediction and you have to see how many of them are correct. That is your true negative. Okay, we have two instances of true negative. Shubhi is correct. This 0 and this one. These are my true negative cases. My model has predicted correctly, and the prediction that it has given me, this zero is what? My negative class, true negative. So I have two true negative cases here. False, these two are my false positive cases. Now, false negative. How many instances do we have here for false negative? Now I think it would be clear because anyway, uh, we are only left with limited number of records now. Yeah, it's easy maths. You just have to take a sum of this and get total number of rows and subtract it. Yes, difficult to answer, right? Very difficult. Now that you have calculated for the sample data, if you have these numbers, can you not calculate precision recall and F1 score? Precision recall and F1 score. If you already have the values for this, you will easily be able to put the numbers and calculate precision recall and F1 value, right? Now, let us go ahead. Let me go back to the PPT that we had. This was just an example that I was trying to show you where you can understand how to calculate true positive, true negative, given that you already have the actual and the predicted values. Now, let us move ahead with some more examples to understand that for a particular problem statement, how do you deal with improving the performance of your algorithm? What kind of uh, you know evaluation metric is more important in certain cases for you? So let us take this example, and it's a very popular example and you will see this in real world as well. So let me go back to this spam classifier. Back to our original question. Spam classifier, we all get emails. Let us say that I recently got a job offer, and the job offer related email that I got, it actually got marked as a spam, as a spam. Or it is not a spam, but Gmail marked that as a spam. It was an offer letter, and I was supposed to submit my documents up to a certain date, and I missed out on that just because it was marked as spam. What kind of uh, confusion in confusion metric? How will you put this? Is it false positive, false negative, true negative, whatever it is you feel? What is this? If actually it is not spam and the model says that it is a spam, and because of that you missed out on a offer letter. True positive, true negative, false positive, false negative. False positive, absolutely. Why? Because The model has given incorrect prediction, that is why we are calling it false, and the prediction that it has given is a positive class, because if PAM is a positive class, this is what we are concerned with. So it is my false positive case. In spam classifier in industry, people usually try to focus on reducing this error. False positive error should be low. Okay, this is their major concern. False negative, even if it is a little higher, that does not matter as much as this false positive. Okay, now, because what will happen is, suppose false negative would mean that falsely predicting a negative class. Negative class is what? Not spam. Actually, it was a spam, but the model said it was not spam, so it came in your general mailbox. What you can do is that you can just go through that email and you can decide to mark it as spam, right? But at least, so this is not a concern, right? I can go through the email and I can mark it as spam. If it has by mistake by a model predicted as not spam, I can still mark it as spam. This will not cause an issue as much as this false positive, because I can miss out on some very important email, some work related email or some job related email, which should not happen. So in this, we would want to minimize false positive. If false positive is a very important metric for me to minimize, which evaluation metric should I be concerned with? In which equation do you see false positive? In precision or in recall? You have the equation in front of you. In which of these equations do you see false positive? Quickly. False positive? In precision or recall? Where do you see false positive? Precision, absolutely. So it means that in this case, you would want to improve precision of your model. Precision is important metric and you would want to improve this in your model for this particular problem statement. Similarly, there can be instances where you would want to improve recall. What exactly recall equation is? Let us go back to the equation. In recall, we have false negative, which means that we are trying to predict negative class and it's a wrong prediction. I'll take an example. Let us say that in a hospital, there is a cancer prediction algorithm. Using that cancer prediction algorithm, doctors are generating report for patients saying that whether or not they have cancer. Now, let us say that a patient went into the hospital and scanned or shared all the reports or something, using which finally this cancer prediction machine learning algorithm said that the patient does not have cancer, no cancer. But let us say that the patient actually had cancer. So this kind of scenario is what? This is my false negative. So the prediction is wrong, definitely, because the patient had cancer, but the model said it does not have cancer. So it's a false prediction. And the prediction is my negative class. Cancer is my positive class. No cancer is my negative class. So this is a false negative condition. You should avoid this kind of condition in medical cases. Why? Because let us say that this person was actually feeling sick, but now because the report had said that he does not have cancer, he will go back and he will relax. He will feel that, okay, I'm just overthinking and I should not, worry that much. So in that case, he is going to lose a lot of time which he could have invested in going through treatments to get better. But just because this one prediction came out wrong, we probably have cost a human life. That is why false negative is very dangerous or hazardous in this kind of situation, whereas false positive is not that much of a concern. Why? So let us say a false positive means that the prediction is this, but the actual value or the actual situation was that the patient had did not have cancer, but the prediction was a positive class. This is not a problem for us. Why? Because if my model is saying that the patient has cancer, but the patient feels that he is very fine. He doesn't feel like having any issue. What he can do is that he can go and have second opinion, or he will just go with other reports or tests as well. He will recommend, he will go to other hospital or doctors as well, right? He will take another opinion definitely if the report says that he has cancer and he feels that he's feeling absolutely fine. So this is not hazardous, but this scenario is hazardous in this case because it can cost human life, right? So, depending on the problem statement, you have to determine, or probably you'll sit with your manager to understand which kind of evaluation metric is more important, or which kind of error should be focused more on in order to minimize that. Eventually, in any kind of machine learning algorithm, your focus would be to minimize the error. In this case, what are your errors? False positive, false negative. In some cases, you would want to minimize this. In some cases, you would want to minimize this. If you're trying to minimize your false negative, that means that you need to reduce, you need to work on your recall should be high. If you're trying to minimize false positive, your precision should be high. This means that you're trying to improve your precision. If you are working on improving or reducing false positive, it means that you're working on uh, this precision metric. But there can be some cases where both false positive and false negative are crucial, and you need to work on minimizing both the errors. That kind of situation is your F1 score. So if you are working to improve your F1 score, that means that your stakeholder wants to have both false positive and false negative as much less as possible. So this kind of situation relates to this. Now, let us go back here. Now, there are two very simple terms. False negative is more important to minimize, or it depends on data and situation. Not data, I would say. It depends on situation, the problem statement that you're trying to solve. All right. Now, we have something which is called as sensitivity. Sensitivity. Sensitivity is nothing but it is exactly same as recall, and is also called as true positive rate. All of these three terms, recall, true positive rate, and sensitivity, are exactly same. If you look at the formula as well, you'll be able to understand that it's exactly same as we had in recall. So, but why then this is the case that we have altogether a different metric? The reason is that in medical field, in medical field, people, instead of calling it as recall, they call it sensitivity because it's a sensitive metric for them. So that is why they just call it as, in medical research or medical related algorithms that people are developing, they call this recall as sensitivity. That is the only difference, but otherwise it is same thing. Another metric that we have here is specificity. So this is your true negative rate. Let me just go back here. So this was your true positive rate. We have true negative rate as well. And this is called as specificity. Specificity. Now the formula is very intuitive, and if you're going to look at it, you will easily be able to understand what is happening. So let me just go back. Let me copy the formula and we'll use this to understand what this actually means. Okay, let us draw our confusion matrix that we used to have. So this is my spam, not spam. Same example, not spam, spam, not spam. This is my true positive, uh, true negative, false positive, false negative. Now this true negative rate, or we also call it as specificity, this talks about in the denominator. Let us focus at what exactly do we have in the denominator. So true negative plus false positive. This is what we have in the denominator. And what is this? This is total number of actual actual negative class, negative classes. In my data, how many data points I have where the output is a negative class. In case of not spam classifier, it will be not spam. This is my negative class. So I'm trying to understand in my data how many data points are actually not spam. So, and you're using that as a base to calculate out of all of this how many your model is able to correctly classify. Not spam, not spam, actual and predicted. Out of all the actual negative classes, how many of those your model is able to correctly predict? That is your true negative rate. And with the name also, you will easily be able to understand, because you're trying to understand the rate or the proportion with which your model is correctly able to classify your negative class. Negative class. True means that your model is making correct prediction, correct prediction. Negative means that prediction is for negative class. Rate is just getting a ratio or the proportion. This is your specificity. You should not memorize these formulas, but if someone shows you this, you should be able to tell them what this formula means. Is in business sense, you should be able to tell them about it. Okay. Now, let us talk about ROC AUC curve. And we are going to plot this ROC AUC curve using the hands-on coding as well. We already have a library using which we'll be able to plot this. We'll have to write some bit of lines for this. We'll have to use matplotlib, c1, all of that as well, along with sklearn inbuilt library. But we will be able to understand this using hands-on coding as well. But in theory, if you have to understand this, let me just copy the graph. It will become really easy for you all to understand from this graph. Okay, let me put it over here. Let me see if I can. Yes. All right. This kind of graph, when you're plotting, you call this as ROC AUC curve. Using this graph for any classification kind of problem statement, you will be able to understand if your model, the model that you have built, is it good, bad, worse, excellent, satisfactory, whatever it is. Using this graph only, you will be able to clearly tell. Also using precision recall F1 score, you will be able to tell. But usually if you have to show it to stakeholders, you would use visualization. So this is where you can create a visualization to show it to your stakeholder, and you can then tell them that yes, my model is doing good. But what is the idea behind ROC AUC curve? The idea is to compare your model, the model that you have built, with a baseline model. I think in the starting, so let me just write down what I said. The idea behind this is to compare your model, the one that you have built or you have trained. You compare with baseline model. Baseline model. I think when we just started at that point of time, I had told you about baseline model. Baseline model is when you are not using, let us say that I don't know data science, I don't know machine learning, I know nothing about coding, but someone comes and gives me a data and tells me to do a prediction. So for example, someone gives me that number of hours number of hours a student has studied. I have data point for that: 8, 5, 3, 2, 6. These data points I already have. And the marks that the student has got: 70, 35, 40, 60, and 28. Whatever that is. I have been given this data, and someone tells me that can you predict for a unseen data point, a new number of hour data has come in. Can you predict what will be the marks that particular student would have got? Can you do the prediction? So, for example, number of hours that the student has studied is 10. Now there is no data point for this, and I have to do a prediction for this data point. I don't know machine learning, I don't know data science. What I can do is that simply I can take the average of all the values, all of these values. I'll take the average, and whatever that average is, I'm going to say that yes, this is my prediction of all the historic marks, whatever the average is, I'm going to say that yes, around somewhere around this, this particular person would be getting this kind of model, where you are just predicting average value as the predicted data point. This is your baseline model. Baseline model. Why we are calling it as baseline? Because we compare our models with this baseline model. If your model is dumb so much that it is not even able to perform better than this baseline model, then it's good for nothing and it should not go into production, right? So this is why we compare it with a baseline model, because in the baseline model you don't have to do anything, no machine learning is required. You can just use the average of all the historic data and you can predict for any unseen data. So tomorrow some new data point comes, you will say that okay, take the average of whatever data points we have until now and this will be the prediction. This is a dumb way, but if the model that you have created is not performing even better than this baseline or dumb model, then it's not a good model. This dotted line, this dotted line that you're seeing over here, this is basically representing AUC of 0.4. AUC is nothing but area under curve. So you will calculate the area under this straight line, and this is your area under curve, and the value for this is 0.5. 0.5. If AUC value for your model is less than 0.5, which means that it is falling somewhere around here, then it is performing worse than the baseline model. So this AUC of 0.5 represents the performance of the baseline model. So if your curve is coming below this, that means that your model is dumb and it should not go into production. It's a very bad model and you should not be showing it to your stakeholders. But if your AUC is greater than 0.5, so for example, these cases, AUC of 0.65, area under curve is nothing but area under, so I think I did a little bit, okay, area under this particular curve. So this will be your 0.65. If I talk about AUC value for the upper curve, the area will be taken for this entire thing. And this area is nothing but 0.9, which they have already given. So this is good model. This is good model. Whatever AUC value is for this lower one, this is a bad model. So this is a questionable model for me because it is not performing better than my baseline model. This is how you can interpret ROC AUC curve. Now, ROC AUC curve is nothing but just the ratio of true positive rate with your false positive rate. You just have to take the ratio of true positive rate and false positive rate. This is how you are going to get your ROC AUC curve. So basically on the graph that I had pasted, I can paste it again, I think, because it will be copied. Yes. On this graph, on this X axis, so here you have true positive. Let me change the color. Here on this X axis, you have true positive rate. Here on this Y axis, you have false positive rate. And you are just plotting for this. If your curve is above this dotted line, it's a good model. Otherwise, it is a bad model. This set of value that you have been provided here to check the quality of the performance of your model, usually you can use this, but not everywhere the same quality test is going to get conducted, because it depends on stakeholders to stakeholders and problem statement as well. Some problem statements are really difficult, and in those cases it may not be at all possible to get AUC value in this excellent range. So if it's not possible, it's not possible, right? So depending on the problem statement and the data you have exposure to, there are certain standards which you will have to follow. Only after that you'll be able to show it to your stakeholders. So this is your ROC AUC curve, a way to compare how good your model is doing compared to the baseline or a dumb model. All right. So here you can see this is a random classifier. Random classifier means that randomly you are just predicting average as the prediction value. That is your random classifier. And this is your better model. compared to this baseline model, and this is your best or perfect model. Here, this at the top, because this will give you AUC, area under the curve of 1. So this is your best model, but usually you will never get this. Let us say that there was a exam, MCQ exam, that was getting conducted in a school or university. In that exam, you have got every student who has appeared has got a sheet wherein they have, for every question, question number 1, 2, 3 until 100, they have got options like A, B, C, D. Like this, if for every question there are 4 options. You can consider this as binary multi-class classification. We have 4 different options in the output. Let us say there is a student who is going to mark this C as a response in all the questions without knowing, without reading the question, without understanding the question. He is randomly going to mark C as a response. And let us say, despite doing that, he has got 40% marks. 40% marks just by randomly marking one response as the output. Now, this is, you can consider this as your random classifier. Even by randomly predicting certain value, you are going to get some risk, some accuracy will be there definitely, right? After evaluation, the marks will be given to this student as well, right? And you have correctly understood the questions, correctly solved the questions, and after that you have scored, uh, let us say 60% you have scored. You can compare your marks with this student's marks, and then you'll be able to understand if you're doing good or not, because this person randomly went ahead and hit the responses, but you have prepared, you have gone through the questions, you have solved the question and everything. Same goes for machine learning as well. In machine learning, if the algorithm randomly goes ahead and does the prediction, so for example, if I'm doing a dog cat lizard buffalo, when I trained this model, when I trained this model to classify these output variables, at that point of time, the majority of the data points that I had was for cat. So my machine learning algorithm will feel that, okay, if I go ahead and keep on predicting cat for majority, I'm going to give correct responses, right? So that is your random classifier. It is going to output the uh, mode, mean median mode, we all have studied. It is going to output the mode value in your data set on which it has been trained for all the upcoming data points. If that happens, then also it will have some accuracy score. Let us say that the accuracy score was 40, 50%. Then, if that is the case, if you are then going to give new data points, it is always going to predict this value. You have to compare this kind of dumb model with a model which you have optimized, you have trained it on variety of data set with different examples for dog, lizard and buffalo as well. On that model, you have to then get the accuracy. For example, on that model, you're getting the accuracy of 40%. That means that the model that you have built, even after giving these many different examples for different classes, you are only getting 40%. This is even worse than the dumb model. So this is why we are comparing it with AUC of zero point 0.5. AUC of zero point 0.5 represents a random classifier, which means that randomly some output is getting generated by the model, probably based on the data that it has been trained on. Right? If it is biased, if it is unbalanced, it is going to give this kind of prediction because it has not understood or generalized the data. It is just going to give random output. So your model that you have trained should always be better than this kind of dumb model. Here you can read this. They have written the same thing. Area under the curve is equal to 1 is a perfect model, which usually you will not come across. Area under curve is equal to 1, which means that your model performs exactly same as a random classifier or a random guessing model. Area under curve less than zero point 0.5, which means that your model performs even worse than the random guessing. So this can usually be due to the problem in the data. Probably there are not enough instances of data points for the other classes, and because of that, your model is not able to generalize and predict correct responses. Now, let us talk about the problem that we have here. What and why did I say that my model will go ahead and predict the highest frequency or more frequent occurring output? Why did I say that? Because it could have happened that in the original data, the majority of the data points that I had was for cat. I did not provide to my model the data points where it can learn the patterns to recognize dog, lizard, or buffalo. So that is why my model is only able to clearly understand cat related features. That is the problem of imbalanced data. Imbalanced data. Data. So let me just show you. So for example, if in my data I have 1,000 data points, in those 1,000 data points, for cat I have 800, for dog I have 50, for lizard I have the 30, and for buffalo 120. These are the number of data points that I have for all of these target variables. This is a multi-class classification. Now, don't you think that my model will easily be able to understand how to predict for cat, but not for dog, lizard, or buffalo? You can relate it with a day-to-day use case. If I am solving 50 questions in front of you on linear regression, but I'm only solving one question in front of you on all the other algorithms, all other supervised ML algorithms. Don't you think you will easily be able to in future solve questions related to linear compared to other algorithms? Why? Because I have shown you enough examples for this, but not enough examples for this. You will face problem when solving the questions related to other algorithms, but you will solve less problem when solving the questions for linear. This is the problem that not just we humans face when we are exposed to limited number of examples for something. We do not understand how to generalize that particular concept. Similarly, machine learning is also an algorithm which is based on mathematical equations, and it will only be able to understand if it has been exposed to enough instances for every target variable. This is the problem statement which we call as imbalanced data problem. Imbalanced data. Exactly. That's right. So, and I was going to take that example as well. For spam classifier, spam classifier, or not just spam, but even for fraud detection, fraud detection, you are going to get less number of data points for the positive class. So when I say positive class, spam is a positive class, not spam is a negative class. Fraud is a positive class, not fraud is a negative class. This you will have less number of data points, because out of all the emails that you get on a daily basis, very few of those emails are going to be spam. So you will have very less occurrence or very less instances of positive class here. So in this case, definitely you will have imbalanced data. Similarly, for fraud detection as well, the number of fraud transactions that happen compared to the number of overall transactions that happen on a day-to-day basis for an individual person or individual bank or services is very less. Fraud transactions are not that frequent. So it means that you will have less number of data points for this as well. So these two examples fall within the examples or the problems or the problem statement where you will come across imbalanced data, which means that we need to deal with this imbalance so that our model does not get biased towards one prediction. In the example that I had taken, where I was giving more instances of cat and my model was going to predict cat for majority of the data points, that is a biased result. Your model will get biased towards one output, towards predicting just one output. We do not want that to happen. We want our models to be as generalized as possible. So this is why we need to deal with imbalanced data set. Now, this is one problem. The other problem that we'll have is overfitting. Overfitting. Because your model at the time of training is going to perform good, but at the time of testing, it's not going to perform well. train accuracy is going to be high, whereas test accuracy will not be that good. So overfitting problem will exist if you have imbalanced data set. The other problem will be when you're trying to train your data, you will face issues when you're dealing when you're doing this training, because you have different proportion of data points in your data set. I'm going to talk about this when I'll touch upon cross validation. At the time of training, how you're going to have issue when you have imbalanced data. We'll talk about this in cross validation, which is the next topic that we have to touch upon. And the last issue that you're going to have when you will deal with this is definitely performance decline. Decline. Your model is going to perform poor, and it will not be able to generalize the predictions. Now, what are the different ways using which we can deal with this kind of problem of imbalanced data? There are two methods in general. One is oversampling and undersampling. So, undersampling is one way to deal with it. Oversampling is another way to deal with this kind of imbalanced data problem. Okay. Now, within undersampling method, what are the different techniques that we have in order to deal with imbalanced data? First is random undersampling. Random undersampling. In oversampling also, we have a technique which is called as random oversampling. Oversampling. The second technique in undersampling is atomic link. Atomic link. Here we have something which is called as smooth. Smooth. We have edited nearest neighbor. Here we have Edison. Edison. We are going to now talk about all of these six techniques, or six, I would say rather, six ways to deal with imbalanced dataset problem. The techniques to deal with imbalanced dataset. So the first technique, let us start with undersampling. Undersampling. Undersampling means that you are trying to reduce the minority class. So two terms you should be very familiar with. One is minority class. Minority class. One is majority class. Majority class. If your data is imbalanced, you are definitely going to come across minority and majority class. In spam classifier, if I have more number of data points for not spam type of email, then my minority class will be spam class. My majority class is going to be not spam. Similarly, in case of fraud, transaction or fraud detector related machine learning algorithm, my minority class will be my fraud class, whereas if I have majority number of data points correspond to not fraud transactions, then not fraud is going to be my majority class. I'll take a simple example. Let us say 1,000 data points I have. Out of that 1,000 data points, I'm talking about spam classifier. Spam classifier. I have 100 instances or 100 data points for spam, and 900 data points I have for not spam. Not spam. Now I can clearly understand that this is my minority class, whereas this is my majority class. I have to deal with this problem. One way is to do undersampling. Out of that, to perform undersampling, the first approach that we are going to talk about is random undersampling. Random undersampling. In random undersampling, you are going to get rid of the data points from the majority class randomly. If I have to balance this data, that would mean that how can I balance it if I have to undersample? Undersample means that you're going to reduce the number of samples. So out of these two classes, in which class data point you're going to reduce the data. If you have to perform undersampling, you're going to reduce the number of data points. Which of these two classes you will reduce the or remove the data points for out of these two? Spam, not spam? Majority class. Exactly, Shubhi. We are going to remove the number of data points from this not spam class until we get 100. We are only left with 100 data points for not spam, because we have to match or we have to balance this data. If in my data minority class is only having 100 records, I need to undersample, I need to reduce the number of samples from the majority class until it reaches or until it matches my minority class. Now, after performing undersampling, I'm going to have only 200 data points in total. And in that 200 data points, 100 will be for spam, 100 will be for not spam, because I numbly will get rid of 800 data points to balance this data. This is random undersampling. Now, let us talk about the other one, which is atomic link. Very less common. This one is not that commonly used. How it works is that it also does undersampling, which means that it is going to bring your majority class to the level of your minority class. But how it does the removal? Yes, not exactly same. You don't need to have the exact same 100 records, but somewhere nearby. It should not have much difference. Even if it has like 100 and 120 number of records, it's fine. Yes, 100 to 100 is very high difference. So 60-40 ratio is also very high difference, and you're talking about 50, like 200, 2 is to 1 ratio, right? That is very high ratio. That should not happen. So, and you're not going to do that manually. You will use sklearn library to perform this undersampling, so you will see how much it reduces the number of data points and all of that. So you don't have to manually think about how much you should reduce it to. All of that is not our concern. Tonate link also performs undersampling, but the way it performs undersampling is different. Are these changes in the sample permanent? Shubhi, what you will do is that you will have your initial data frame after doing pd.read CSV, read CSV, right? You will have your data frame. If you use sklearn library to perform random undersampling, you can store it in a different variable, df copy, right? Yes, exactly. You can create altogether a different data frame. You can store that undersampled data in this data frame, so your original one will be preserved. So it's not going to make any change to the original data if you don't want it to. Okay, so atomic link, it also does the undersampling, but how it does the undersampling, let us talk about that. It is going to remove the data points which are hard to classify. Hard to classify. Classify. The data points which are near the decision boundary. Near the decision boundary. What I mean is that, let us say that this is my, in my data, spam, not spam are the two classes. If I create a distribution plot or a scatter plot to get the distribution of my data, let us say that the distribution looks something like this, where I'm easily able to separate my spam classes and not spam classes, right? So if this is the kind of distribution, this is my spam class, this is my not spam class, and I'll say that, okay, this is my decision boundary. Anything which is beyond this boundary is my spam. Anything which is beyond this boundary is my not spam. Okay, now what type of data points will be hard to classify? So let us say there is a data point here in majority class which is very close to decision boundary. Very close to decision boundary. These will be hard to classify data points, because if my decision boundary just shifts by a little, then these points are easily going to get misclassified as spam. So Tomic link will do the undersampling, wherein it is going to get rid of 800 data points from this not spam, but out of these 800 data points, it is going to focus more on getting rid of hard to classify data points. This is how it prioritizes the undersampling in your data. Now, third technique that we have is edited nearest neighbor. Edited nearest neighbor. This is just an extension of your Tomic link, just an advanced version of Tomic link, wherein you are still going to first of all get rid of the hard to classify data points when you're doing undersampling or removing the data point from majority class. You are still going to do the same, but just that here you're going to take into account the nearest neighbor. So, for example, if I choose nearest neighbor is equal to 3, then I'm going to, from a particular data point, I'm going to get rid of the 3 nearest neighbor data points. So if this is the data point and I want to remove 3 nearest neighbors from this, these are the 3 nearest neighbors. So I'll get rid of this. So I have put it on the wrong side of the decision boundary, but you can, I think you would have got the idea, right? So if you just, so let us say that this is a hard to classify data point, and when I'm performing ENN and I've decided that I'm going to take nearest neighbor as 3, then not just this data point I'm going to get rid of, but 3 nearest neighbors from this data point also I'm going to remove altogether. So this is how ENN performs under sampling. Just that it's a little advanced from Tomic link, but it does the same thing. Criteria is different. Now let's talk about oversampling. Oversampling. The first technique is random oversampling. Random oversampling. Random oversampling. Yes, Thalish. In ENN, these steps are going to remain exactly same as Tomic link, just that here instead of randomly getting rid of hard to classify data points, it is going to also take into account nearest neighbors. So if I have decided to get rid of this because it's a hard to classify data point, I'll not just restrict myself at removing this hard to classify data point, but along with this data point, I will also remove the 3 nearest neighbor data points from this hard to classify data point. Because I have decided nearest neighbor is equal to 3. This is a parameter that you can take. This is dependent on you. You have to decide this value. If you decide it as 3, along with this hard to classify data point, you will remove 3 more closest data point to this one. So this is the only difference. You are also considering nearest neighbor when you are trying to downsize your majority class. I hope this is clear now, Alish. Let us talk about random oversampling. Same example. I have 100 data points for spam classes. For not spam classes, I have 900 data points. If I have to do oversampling, it means that I have to increase the number of samples of the minority class. Over means I'm going to introduce more number of samples of data. But for what? If I'll add more data points here, I'm just going to add more to my imbalanced data problem. So, which means that clearly I have to add more data here. When I'm doing oversampling, I'll do it for my minority class, on my minority class. So here, if I just add 800 data points, don't you think now this is balanced? 900 and 900. Now this is balanced. So all I'll have to do to oversample this is to introduce 800 sample data points in my minority class. How I'm going to do this in case of random oversampling? You're going to randomly introduce 800 data points, random data points. Let us talk about the other way of doing oversampling, smooth. Smooth. It is also called as, I mean, if you just extend the full form of this, it's synthetic minority oversampling technique. Oversampling technique. Technique. Clearly, you can understand by this extended full form of this, you're trying to create synthetic data points for your minority class, right? Now, how you are going to create this synthetic data point or the artificial data point, because you have to add more number of data points, how you're going to do this in smooth. Let us talk about that. There's a mathematical equation that you will have to follow in here. So Let us say that this is my decision boundary. These are my spam classes. These are my not spam classes. I'll have more number of data points for not spam. So less instances for not spam. Sorry, for spam. Spam, not spam. How you're going to create synthetic data point here is that you're going to consider this particular data point. Let us say this is my existing current data point. I'm going to take the difference of this data point from any other data point that I have. So let us consider this as my x1, this other data point as my x2. You're going to take a difference of these two data points. Whatever that difference is going to come, you're going to multiply a variable called lambda. This lambda is a small value. It will range between 0 and 1. You're going to multiply it by lambda. Once you have multiplied it, you're going to then add it back to the original data. So this data is my x1 data, x1. And this any other data, you can randomly consider this as x2. You are going to calculate the difference between x1 and x2. On that difference, you're going to multiply it by a factor. That factor is called as lambda. And lambda can range between 0 and 1. This is not for us to decide. We don't have to decide its value. And once you have done this calculation, you will add it back to the original data point x1. Whatever this calculated value will come, let us say that this is my xi. Whatever that mathematical value will be, that is your newly created synthetic data. Synthetic data. This is how Smoot is going to create synthetic samples of your minority class using this kind of mathematical equation. Now, let us talk about the last technique in oversampling. Once we have wrapped up all the techniques, I'm going to tell you in which case you should use what kind of sampling technique. We'll talk about that as well. And that will summarize this imbalanced data problem and how to deal with it. The last technique that we have in here is, I think we have covered Smoot. We have Edison. So this is adaptive synthetic oversampling technique. Oversampling technique. This is an advanced version of Smoot. The way we saw that there is an advanced version of Tomic link. What is that advanced version? Edited nearest neighbor. Similarly, in oversampling as well, the advanced version of Smoot technique is Edison, adaptive synthetic oversampling technique. Here also, the idea and how it does is that it is going to oversample for hard to classify data points. So if I have these, and let us say that in your data, it's not a linearly separable data, which means that there are some data points which are closer to each other. So for example, if this is a spam data point because it is on that side of decision boundary, and let us say that on this side of decision boundary, this is my not spam data point. Now these two data points, because they are very close to each other compared to their distance with their own respective group, this distance is less, right, between these data points. So it can happen that your model can misclassify these data points. So Edison is going to generate the synthetic data points, but for hard to classify data points. So the data points which are near to the boundary, those data points, basis those data points, it will generate the synthetic samples of data such that your minority class now has more number of data points to learn the pattern from. This is adaptive synthetic oversampling technique. Now, let us talk about what you're going to use in which case. Summary. Let us say you have a small imbalance in your data. The imbalance is very small. So for example, 60-40 is the ratio of data point that you have for both the classes, or it can be 70/30 is not a huge imbalance, I would say. That kind of ratio, if you have, that is called as small imbalance. The definition of small imbalance will change basis the industry data point and the team that you're working with. But generally, I'm just giving an example. This is not hard and fast, and this is not a rule. But if your data set has very small imbalance, in that case, you can go ahead with random oversampling, oversampling, or random undersampling. Random undersampling. Undersampling. If there is a small imbalance in your data, let us say that there is a severe imbalance in your data. Severe imbalance. Spam classifier, usually the kind of imbalance will be severe only. In fraud detection as well, usually the kind of imbalance will be severe only. When I say severe, I'm talking about 99:1. For 99 data points in not spam, you have only one data point in spam class. Like that, if this is the kind of ratio, this is usually considered as a severe imbalance. So in this type of situation, you should use smooth and or Addison to generate more number of data points if you have severe imbalance. Next, now if I have to just give an example for the severe imbalance, when COVID had hit, at the time of COVID, if people wanted to capture the virus samples from people, initially there was less outbreak, so less samples were available, and people, researchers were not able to test it because they have very less number of samples. So less sample for COVID, that's a very severe imbalance compared to the population data that we have. If there is less sample of COVID, and we are trying to use this to research and come up with some medication for this kind of thing is a severe imbalance example that you can think of. But after that, obviously, there was a huge outbreak, and a lot of samples could be calculated. Other situation is, let us say that I have large data set. I have 10 million, 20 million, 2 million, 5 million records in my data. Usually, you would consider that as a large data set. In that case, you can perform undersampling to deal with imbalanced data. Why? Because undersampling is very quick process and it requires very less computation as well. And you already have a large data set. So if you perform undersampling, even after losing some number of records, you are still going to have enough number of instances using which you can train your model because you have a large data set. So undersampling is not going to impact the performance of your model if you have a large data set. Another situation, let us say that you have a complex decision boundary. When I say complex decision boundary, I'm talking about non-separable data. So, for example, the data that I have, these are my spam classes and these are my not spam classes, but there's a lot of overlap in my data. Some of these spams are closer to some of these not spams, like this. So this decision boundary is not able to correctly classify my data point. And in that kind of situation where your data is not linearly separable, the classes are mixed up. In that case, you should use smooth plus tomic link. Tomic link. There's a library in IMB Learn. So IMB Learn is a library for imbalanced dataset related modules that you can utilize to perform oversampling and undersampling. Inside this IMB Learn, there is a specific class which is, I think, smooth tomic. Tomic. This is nothing but a combination of smooth and tomic link. So if your data set has a complex decision boundary, it is not linearly separable. When you plot a scatter plot, you are seeing this kind of graph, like this kind of pattern, where it cannot be separated by a straight line. That in that situation, you should use smooth plus tomic link. It is available in imblearn.combine. Combine. You can use it to produce more number of samples for your data, and you can deal with your imbalanced dataset problem. Okay, these are some of the pointers which I have told you based on the general thing that usually you will see in real industry problem statements. There is no hard and fast rule for what technique you should use. Whatever works for your data in your problem statement, go ahead with that. But usually these are some of the things which I've seen people using. I've been with them, I've worked with them in the projects, and I've seen and I've also used these techniques basis this kind of criteria. So you can just follow this kind of pattern. Otherwise, you can experiment as well. There's no harm in using more than one types of oversampling, undersampling technique and checking the accuracy for all of those techniques. And whichever works best for you, you can go ahead with that. With time, you will understand what works best for a given data and problem statement. Now, we are going to start cross validation technique. Let me go back to the PPT. And so here we have random undersampling. So you're going to reduce 90 samples of data to match with the minority class, which is your 10 sample data point. Random oversampling, here you're going to increase the number of data points for the minority class where you just have 10 samples, and you're going to match it with the majority class so that you have balanced data. Then we understood SMOT and Addison as well. So you can see the mathematical equation that is being written here, x1 plus lambda times x of ni, which is a data point, and you're subtracting it from x1. And lambda can range between 0 and 1. So this Addison as well, we have understood. There are two other techniques that we spoke about, which is Tomic, link, and edited nearest neighbor, that are usually not covered, and usually nobody uses that in the industry. That is why it's not being covered in the theoretical part as well. But I just covered it because I wanted to talk about those techniques as well. Now we are going to cover cross validation. What is cross validation? Why do we use cross validation? And what are the different ways to perform cross validation? And with that, we are going to end today's session. We'll not be talking about the hands-on demonstration. We'll start that on Friday. So cross validation is the last topic that we have for today. Let us say that I have a data wherein I have 1,000 rows, 1,000 records in my data. I am going to perform a cross validation of 5. So I'll just write it here, cross validation of 5. In industry, generally, you will see cross validation of 5 is a standard cross validation. You can choose between other values 5, 6, 7, 8, 10, 20, whatever you feel like you can do. But generally, people go ahead with cross validation of 5. So in this case, we are going to do the same cross validation of 5. What this means is that you want to subject your model to different test data, because when we do train test split, at that point of time, we specify the test size as 0.2 or 0.3, right? Something like that, which means that 20% of the data or 30% of the data we are leaving as unseen for the model so that we can later test the accuracy of our model. That is our test size. But if I have only 1,000 row, then 20% of this, 20% of this, how much it will be? Just do a quick calculation, everyone. I've written it in front of you. How many data points will have? 200? Exactly. 200. Only 200 data point I'm going to leave as unseen data for my model. Based on this small data, I will not be able to capture how good my model is doing. It could be the case that, okay, my model is going to do good on this 200, but probably not going to do on the 800 data points that I have, the one on which I trained my model. Probably those were hard data points. Those data points were hard to classify, right? I already trained my model on that. So now I'm showing easy ones to my model. In that case, we will never be able to understand the absolute performance of my model. So what researchers said that let us not limit ourselves with the data that we have. On the even the small data, we will find a way to understand or generalize the performance of our model. So what we did, we invented cross validation. In this, when you're doing cross validation of 5, it means that you're going to create 5 folds of your data, 5 chunk of your data. You can just consider this as 200 data points are here, 200 data points are here, 200, 200, 200. 5 chunks. You're going to split your data. like this. Once you have split your data, then one by one in fold one. In fold one, what will happen, or iteration one, you can consider that as well. You're going to consider the first fold of your data as test data, and the remaining four chunks or four split, you're going to consider that as your training data. You're going to train your model, whatever that model is. Linear, logistic, cross validation is not just for logistic regression or not just for classification problem statement. It is applicable for even regression problem statements. So cross validation is a technique. It can be used in linear, logistic, or any kind of machine learning algorithm, supervised one that you're going to see. So in this one, this is my training data. I'm going to do model.fit, model.predict. So this is my train data. On this data, I'm going to do model.fit. And on this data, I'm going to do model.predict. Model.predict. Basis the prediction, I'm going to then get my R2 score value. This is just fold one. Next, what will happen is that I'm saying that, okay, now I have trained my model on this set of data. I want to change the training data, but I don't have the advantage, or I don't have the leverage to get more data from my team. I have limited data only. What I can do is that I can shuffle my data. Not shuffling exactly, but because I already have split my data, I can now train my model on this, and this. This will be my training data, and this is going to now be my test data. I'll keep this as unseen data for my model, and I'm going to train my model on the remaining chunks of data. Now, after doing again model.fit and on this one, you'll do model.predict. You'll get some accuracy. You can compare that accuracy with the actual value, and you're going to get your R2 score again. You're going to repeat this same process. So in fold 3, your test data and training data will change. This will be your test data now, and the remaining chunks, this 3, 1, 2, 3, 4 will be your training data. Now on this, you're going to do model.fit. On this, you're going to do model.predict, and then you're going to compare actual and predicted, and then you're going to get R2 score. Next, fold 4. Here, 1, 2, 3, 4, 5. This will be your test data now. The remaining 1, 2, 3, 4. This will become your train data. You're going to train your model. You're going to do model.fit on 1, 2, 3, 4 block of data, and you're going to do model.predict on this chunk of data. You are going to compare actual and predicted. You're going to get your R2 score value. Last, fold 5. Here, 1, 2, 3, 4, 5. 1, 2, 3, 4. This will be your test data, and the remaining ones will be your train data. You're going to do model.fit on this, you're going to do model.predict on this, and you're going to compare actual and predicted, and basis that you're going to get your R2 score. Once you have ensured that your model now has been tested on all possible set of data that you have, now you can go ahead and calculate. With surety, you will be able to now say how good your model is. How to do that? You have R2 score from first fold, you have R2 score from second fold, you have R2 score from third fold, R2 score from fourth fold, R2 score from fifth fold. You're going to just take the average of those R2 score values. This will be your average R2 score. This average R2 score, whatever that is, let us say it is 0.8. This is the average R2 score. Then now you can say with certainty that no matter what test data I subject my model to, it is still going to, on an average, perform with 80% accuracy. Always you have to add on an average, it is going to perform 80% accuracy, no matter what test data I subject my model to. Okay, this is how you can interpret cross validation and what it does for you. You're trying to just be sure that your model is generalizing the pattern and it is going to give good prediction no matter what test data it gets subjected to. Okay. All right. This is cross validation technique. We use it to ensure that our model is doing good. And how it works, I have already shown you now. Okay. Now, let us understand some of these cross validation techniques, some of the methods using which we are going to perform cross validation techniques. Cross validation. First one is hold out cross validation. Hold out cross validation. This is nothing but we have come across this so many times. Whenever we train a model, we do train test split. Train test split. We use this train test split library. In this, we pass our x, we pass our y, we pass our test size, and we also give random state is equal to some value. Random state is equal to some value, right? This is what we pass. Let me just remove this from here. 0.2. This is what we pass in train test split. When you're doing train test split, what happens is your entire data gets split up between train and test data. So now what you will have, 20% of the data will be left randomly, 20% of the data will be selected from your entire data set, and it will be kept aside for testing. Kept aside for testing. So you're putting this data on hold. You're not subjecting your model at the time of training. You're not subjecting your model to this. Whereas you're going to train your model on the rest of the data points, which is your 80% of the data. If you're giving 20% of the test size, it will keep the 80% of the data point for training purpose and the 20% for testing. Randomly, 20% will get selected, and your model will never see this at the time of training. This is your hold out cross validation. You are holding out on a sample of the data so that you can use it later to test the performance of your model. So you can compare it with the school exams. I think in the class we are taught with certain syllabus. We have a certain syllabus which gets covered, certain questions which gets covered. But in the exam, there are different type of questions that will come. Some of them will resemble something that has already been covered in the class, whereas some questions would not have been covered in the class, right? So that is exactly what we are doing here. We are training our model, but we are also keeping some unseen data aside so that we can check how well our model has learned the concepts. Okay. Next type of cross validation technique that we have. Let us go back to the PPT. So this was hold out cross validation. Next is k-fold cross validation. K-fold cross validation. And this is a very common technique and very useful technique that people use in industry, and a very important one as well. In k-fold cross validation, you're going to the same thing that we were doing when we were giving cross validation is equal to 5 or cross validation is equal to 7. This 7 or 5 is nothing but the value of k. You're saying basically 5-fold cross validation. Here you're saying 7-fold cross validation, which means that you're telling that fold my data into 7, split my data into 7 chunks, or here you are saying that split my data into 5 chunks and then perform cross validation. So k-fold cross validation is exactly what I have already covered by taking the value of k as 5. So we have already covered the technique or the approach for k-fold cross validation. And the reason why this is very common is because of very high performance, or usually if you have tested your model with k-fold cross validation, you can be assured that whatever average R2 score you're getting, that is the truth, and you can tell it to your stakeholder, and usually your model will not perform, or your model is not going to deviate from that average R2 score value. Your model's performance will mostly be near that value only, no matter what kind of unseen test data comes in the future. Other technique in cross validation that we have is leave one out cross validation. Leave one out cross validation is something which no one uses in the industry. So this is a very bad cross validation technique. Nobody uses that. The reason for that you will easily understand when I'll give you the example. And I think the name also gives you a clear indication as to why you're not going to use that. It's very computation heavy. Let's say I have 1,000 rows, and 1,000, I'm just taking a small data here. In the first iteration, you're going to leave one data point for test, and remaining 999 records or 999 data points you're going to use for training purpose. In the second iteration, you are now going to leave this one data take this another one data point for testing, and the rest 999, so 998 data points will be here in this section and one data point is here. So you're going to take this 999 data point for training, and you're going to test your data on this one data point. Now if I have 1000 data points, how many iterations I'll have to do before I can actually calculate my average I2 score? How many iterations I'll have to do? If I'm leaving one data point every time for testing and I have 1000 records, how many iterations I'll have to go before I can get the average? Absolutely, absolutely right. Because I want to test the accuracy of my model on every fold of data or every split of data that I have done. In this case, I'm splitting the data on just one data point. The split is on one data point. I have to just leave one data point for testing, right? So this is why it will have 1000 iterations. 1000 iterations, or you can call it as 1000 fold. This is very heavy on computation, and this is super slow, like really slow, very slow. If you don't have GPU, you will not even be able to implement this leave one out if you have a large data set. Unless and until you have GPU, you will not be able to implement this on a large data set. That is why no one uses this technique. And then researchers came out with a slight modified version of this, which is called as leave P out cross validation. Now, as you can see here, the name itself clarifies what we are going to do here. Let us say I have a data wherein I have 1000 rows. 1000 rows. This P is a variable that I can decide. I can choose this P to be 10, 20, 30, 100, 500. Whatever that value is, this P is up to me to decide. You can pass the value of P basis the number of records you have in your data. So you can tell the library, in the library you can pass this as an argument, and you can tell that how many folds of data you would want to have, how many samples of data you would want to leave out for testing. This is up to you. If you give lower values of P, in that case, it is going to be, in terms of performance, it is going to be very similar to leave one out. But if you take a larger value of P, in that case, it is going to be faster, right? So this is up to you. But let us say that I have decided to uh, take this P value as 500. How many iteration or how many folds will happen if I am choosing P value as 500 and I have 1000 records? Exactly. In that case, only two split of data will happen. In one split, you will have 500 rows. In one split, you will have 500 rows. In the first fold, you are going to train your model on this and test your model on this. In the second iteration, you are going to test your model on this, train your model on this. So only two iterations will happen in case you choose P as 500. So I think you have now understood the concept of leave P out cross validation. The other cross validation technique that we have, and this is also a very commonly used cross validation technique, stratified cross validation. Okay. In stratified cross validation, basically here, this type of cross validation should be used when you have imbalanced data. Imbalanced data. If my data is balanced, in that case, I can go ahead with any other cross validation technique. The ones that we have covered, you can choose any one. But most commonly, if you have balanced data, you're going to go ahead with K-fold only, because that's very popular and it's faster as well compared to the other cross validation techniques. If you have balanced data, balanced data. But in case your data is imbalanced, and which is a very common problem in classification type of problem statement, in that case you should go ahead with stratified cross validation. Why? What stratified? Why exactly should we go ahead with stratified cross validation? Is that, let us say that I'm considering this chunk as my train data and this chunk as my test data. And I'm trying to build a spam classifier. Spam is my minority class data, and my not spam, not spam is my majority class. I have 100 data point for this, I have 900 data point for this. This is my minority class. Let us say that when I did train test split, now train test split is random, right? So at the time of splitting the data, in my training set, the 900 data points that it has given belongs, all of that 900 belongs to this not spam. This can happen because randomly the data points are going to split out between train and test. So it can happen that in my training sample, the 900 data points that I have got are all belonging to not spam. All of those are belonging to not spam. Whereas in my test data, I have got 100 data points, and all of those 100 data points are for spam classifier. This kind of situation can come, and to deal with this kind of situation, we have stratified cross validation technique, because we don't want to test our model on something which it has not been trained on. So what we need to ensure that equal proportion equal proportion of data points for both the classes, positive and negative classes, are there in train as well as test. So let us say that in my train data, I have nearly like 40 data points for spam, and in my test data, I have, if I have 40 here, then definitely I'll have 60 in my test, right? 60 data points. This is acceptable because I have subjected my model to learn the pattern from this class as well. Although there is very less number of sample points for the model to learn, but still it has at least been subjected to this type of class. But that kind of situation where all the data points are belonging to just one class, that is not acceptable. So this stratified cross validation ensures that there is nearly equal proportion of data point across both the positive and negative classes. This is what stratified cross validation is going to ensure when you are performing cross validation. In this, the cross validation is again going to happen in the same way. For example, you will take cross validation is equal to 5. The split will happen same way. In fold 1, you will have 5 chunks or 5 split of your data. This, for example, is your initial test data. This is your train data. Same thing will happen. Model.fit, model.predict, calculate the R2 score by comparing actual and predicted value. Same thing. But the only difference is when it is doing the split of train and test, it is going to ensure that the proportion of data points in your train and test belong to both positive and negative class. There is nearly equal proportion of data point in train and test for both the classes. If you are dealing with multi-class, in that case also it should have nearly same proportion of data point for all the classes. Okay, and then it is going to definitely have the same setup process: fold 1, fold 2, fold 3. All of that is going to be the same, just that the internal process, how the split happens for train and test, how the data points are getting kept in these different splits, that will change, because you have to take into account the proportion of data points. This should be used when you have imbalanced data. Highly recommended in that case. Now, the last cross validation technique that we have, let us go back over here. So we have covered leave one out, leave P out, stratified. This is the last one which we are going to cover. Repeated key fold. This is just a advanced version or something which researchers have built on top of k-fold, and by the name of it also you'll be able to easily understand. Repeated k-fold cross validation. What happens here is that, for example, if I have taken cross validation is equal to 5, in the first fold, fold 1, here, along with giving cross validation value, you also have to give another parameter which is called as number of repeats. Number of repeats. So for example, I'll just tell you, let us say that assume that we have taken number of repeats is equal to 3. In that case, what will happen? Let us try to understand. This is an additional parameter which in k-fold we do not have to provide this, but in repeated k-fold we have to provide this. In the first fold, 1, 2, 3, 4, 5. Cross validation is 5. This is my test data. This is my train data. Train data. Now, what will happen is I'm saying that repeat it for 3 times. In this fold 1 itself, I'm going to repeat it for 3 times on the same fold. Test again, this is going to be my test, and the rest is going to be my train. This is my 1 time, 2 time, one more time I need to repeat. One more time I need to repeat. So the same split or the same chunk I have to consider as my test data, but I have to repeat this process for all the folds. So here, but what will change? In this case, what will change is that shuffling will happen. Internal data shuffling will happen. So what can happen is that in this particular repetition is equal to one case, I had some number of data points in this test. When repetition number 2 happened on the same fold, some data points I'm shuffling, which means that some data points from test can go in this, some data points from train data can come here. So I'm shuffling the data. Now, just by doing a small shuffling, I'm able to get entirely a new set of test data. I can consider this as a new set of test data. When we appear for exams, standard board exams, CBSE or 12th exams, usually there is a standard set of question. Most or not, I would say most, but some of the questions are repetitive from the past years, or even if you're giving UPSC exams and all, people go for go with last 10 year, 25 years of questions. The reason is that at least some questions or the concepts will get covered from there as well. So this is the same thing. We are shuffling the data. So we'll be having some data points in test which will come from the original one, but some will come from this train. And some of this will go over in the training side. So we are shuffling the data between this fold, and this is my second repetition. In the third repetition, you're going to do the same thing again, shuffle. Some data points from here go over here, some data points will come over here. This is just fold 1. And when you are saying repeat is equal to 3, if you will give repeat is equal to 4 or 5 or 6 or something, then again shuffling is going to happen how many times? 4 times. Shuffling is going to happen 5 times. This is just fold 1. Same thing will happen in fold 2 as well. I'll just show for fold 2 and you can then generalize it. This will be your test in fold 2, and I'm saying repetition is equal to 3. In the first repetition, this will happen. In the second repetition, same fold will be used for testing this same block. But what will change? Some shuffling will happen. Now, some data points can come in this test set from this training chunks from here, here, or here, right? And some data point from this test can go in these training data sets, right? So we are shuffling the data. In the third repetition as well, again, same thing, shuffling will happen, but we'll keep this chunk as my test. Small shuffling will happen. Some data will move around and about. Okay. Now we will move to fold 3. Fold 3. And same process will get repeated. Now, can you tell me how many R2 score values will be there? I'm not talking about average R2 score. I'm just talking about the R2 score value. How many R2 score values will be there once we have done cross validation of 5 with 3 repetition? So if we just do cross validation of 5, we will get 5 R2 score values. If I'm doing it with repetition of 3, how many R2 score values will be there? Number of iterations is greater than the fold. Number of how is number of repetition? Number of repetition just means that I'm shuffling the data. I can shuffle the data any point, like any number of times, right? Shuffling is a different thing. I can shuffle it 5 times, 10 times as well. Shuffling will just move around some data points from test to train, train to test, right? So it has nothing to do with this splitting of data, right? When I'm doing fold one, in the first shuffling, first time, which is my just the fold one, we call it as first repetition or shuffling, I'll have one R2 score. Then second repetition or shuffling, you will have one more R2 score. Third shuffling, when you are doing or repetition, you will have another R2 score. Because you're going to get the prediction in all of these individual repetition or shuffling, and you're going to compare that with the actual value, you're going to get R2 score in there as well. This is just for fold one, and I have how many folds? 5 folds, and in every fold I'm getting 3 R2 score values. In total I'm going to have 15 R2 score values, and I'll have to take the average R2 score in the end, so that I can say that for surety, no matter what kind of test data you subject my model to, on an average it is going to perform with 80%, 90%, whatever that number is, with that accuracy it is going to perform. So based on this, you're going to 15 R2 score. In this case, you're going to get your final average R2 score. Okay. And with that, you can be very certain that your model will at least perform with this accuracy, no matter what kind of test data it gets subjected to. Let us go back to this here. And we have finished our cross validation technique as well.
You've just finished a live logistic regression bootcamp. Great work. But this is just the beginning. More tutorials and live sessions are coming your way to help you sharpen your ML skills. Tell us what you would like to learn next in the comments. And don't forget to subscribe so you don't miss any updates from Newton School. Keep practicing on Newton School Launchpad. The link is in the description. And well done today. Keep coding, keep learning, and we'll see you in the next live.